Hello there, and welcome to The Sleepy Scientist. This is your quiet corner of the night, a place where you can settle in, let the day drift away, and let your thoughts float a little more gently. Whether you're lying down, dimming the lights, or simply taking a moment for yourself, you're very welcome here. Tonight's journey leans into one of the calmest and most astonishing mysteries in all of science. The way space stretches, softly and endlessly, in every direction. Before we drift too far into the stars, may I ask where you're watching from tonight? It is always lovely to imagine this gentle little community scattered across continents, each person listening in their own quiet moment. And if you're enjoying these soothing explorations of science, I would be truly grateful if you could give this video a like and subscribe to the channel. To those already subscribed, thank you sincerely. If you would be kind enough to tap the notification bell, you will never miss the next time we wander somewhere new in the universe. And one last favour to ask, if you enjoy these deep, gentle journeys through space, I would be delighted if you took a moment to visit my new channel, The Sleepy Astronomer. Your support there truly means a great deal, and you will find the link waiting for you in the description. So as you get comfortable, and as the room softens into evening, let us step into a universe that grows a little more every moment. The question waiting for us tonight is simple, quiet, and strangely beautiful. Why does space never stop expanding? When you look into the night sky, all the familiar stars feel steady, patient, almost eternal. Yet beyond them lies something far stranger. The deeper you look, the more the universe reveals itself as a place in motion, not with rushing winds or swirling currents, but with distances that quietly increase, almost as though space is taking a long, slow breath. This gentle expansion is not something felt in the body or heard in the air. It unfolds across unimaginable distances, over spans of time that stretch into trillions of years. Every galaxy beyond our closest neighbours drifts a little farther away, not because it is speeding through space, but because the space between us and them is growing. To imagine this is to imagine a universe that changes everywhere at once, in every direction, without needing a centre and without needing an edge. Tonight's exploration will follow this subtle motion piece by piece, moving from the earliest moments of the cosmos to the drifting lanterns of the galaxies, from the mysteries of the energy hidden in empty space to the soft question of what the far future might look like. No equations, no hurry, just a calm unfolding of how the universe came to behave this way and why it shows no sign of stopping. So take a slow breath, settle a little deeper, and let your thoughts loosen as the universe opens quietly around you. If space keeps expanding, what does that tell us about the nature of the cosmos itself? The story begins quietly, as many great scientific shifts do, with people looking at the night sky and expecting it to behave the way it always had. For centuries the universe was imagined as calm and unchanging, a vast celestial stage where stars hung in place and galaxies, though unknown at the time, would surely keep to their positions with perfect dignity. The idea of a static cosmos felt natural, comfortable, almost inevitable. Space, after all, looked still to the human eye. Distances between stars appeared fixed. The darkness overhead stretched out like a serene backdrop that never moved. And for a long while, that simple picture rested unquestioned. Even when telescopes revealed the delicate swirls of spiral nebulae, many believed these glowing shapes were nestled within our own galaxy. Little ornaments embedded in a universe still imagined as timeless. But as instruments improved and starlight was measured with greater care, the night sky began whispering that it was not quite as still as it seemed. Something subtle was happening out there, something hiding in the faint colours of distant light. When astronomers studied the glow from faraway galaxies, they noticed a gentle shift in that light. Instead of appearing exactly as expected, the colours stretched ever so slightly toward the red end of the spectrum. It was a small detail, the sort of thing that could easily be overlooked, yet it held the entire story of a changing universe inside it. This stretching, known as redshift, was not a single discovery made in a dramatic instant. It arrived slowly, piece by piece, as if the cosmos were revealing its secrets one careful hint at a time. As more galaxies were measured, a pattern emerged. The farther away a galaxy appeared, the more its light shifted toward a red. It was not a chaotic scatter of data. It was a calm, clear trend. Every distant galaxy seemed to be drifting away, and the more distant it was, the faster that drift appeared to be. At first, this was baffling. There was no reason to expect such a tidy relationship, and yet the evidence grew harder to ignore. Light was telling a consistent story, one woven through millions of years of travel across space. This raised a simple but transformative question. Were all these galaxies actually racing through space, fleeing from us in every direction? That idea felt strange. After all, it would make our own position in the universe oddly special, as though everything were running away from this one particular location. The notion sat uncomfortably with the understanding that humans occupy no privileged place among the stars. Something else had to be happening, something larger and more elegant. Gradually, a deeper explanation began to take shape. Perhaps the galaxies were not rushing through space at all. Perhaps the space between them was quietly growing. Imagine dots on a soft sheet that is stretched gently on all sides. The dots do not move across the surface, yet the distance between them increases. The sheet expands, and everything upon it separates without needing to travel. This was the quiet, revolutionary idea. Space itself might be stretching like an immense invisible fabric. With that one shift in perspective, the night sky transformed. The universe was no longer a rigid stage, but a living, dynamic thing. Distances were not fixed. They could change. Cosmic structures were not frozen. They could drift apart as the space between them widened. Light arriving from great distances carried the signature of this stretching, gently elongated into redder colours during its long journey toward us. This idea did more than explain the growing separation between galaxies. It reshaped the entire understanding of the cosmos. A static universe could not easily account for the patterns astronomers observed, but a universe that expanded slowly, steadily, and almost silently, made sense of everything. Even the faint afterglow of the early universe, the soft radiation filling space, aligned with the picture of a cosmos that once was smaller, denser, and warmer. And so the universe, once imagined as calm and eternal, revealed itself as something more dynamic. Expansion did not roar or burst outward like an explosion. It was serene, steady, and almost imperceptible from within any small corner of the cosmos. On the scale of everyday experience, nothing stretches. Our rooms remain the same size, our neighbourhoods stay intact, our galaxy remains gravitationally bound. Yet across the great cosmic distances between galaxies, the effect becomes clear. Distances lengthen, light stretches. The pattern persists across billions of light years. There is something strangely peaceful about this realization. The entire universe is involved in a slow, gentle drift, a movement so vast and gradual that countless generations can watch the stars without noticing a thing. Expansion is not an event with a beginning and an end. It is a quiet behavior of space itself, unfolding moment by moment. It has been happening for billions of years, and continues happening right now, woven into the very structure of the cosmos. This discovery also changed the way humans understand time. A static universe could have existed forever without change, but an expanding universe carries a story. It suggests a past when things were closer together, a period when galaxies had not yet formed, a time when the cosmos was unimaginably young and hot. By learning that space grows, astronomers realized they were also learning about the origin of everything within it. What makes this chapter of science so beautifully gentle is that it did not arrive with dramatic upheaval, but with patient observation. It emerged from looking carefully at starlight, from trusting the quiet signals carried across millions of years, and from accepting that the universe behaves in ways that might seem counterintuitive at first glance. Expansion is not something felt on the skin or seen with the naked eye. It appears only when the universe is viewed broadly, through long distances and long time scales. And so the understanding settled in. Galaxies drift apart not because they are fleeing, but because space stretches. Redshift is not simply a trick of light, but a record of the universe's steady growth. The cosmos is not fixed, it is unfolding. Not quickly, not violently, but with the gentle persistence of something that has been growing for almost 14 billion years. This was the quiet turning point, a shift from stillness to motion, from a tranquil cosmic stage to an ever-expanding fabric. The discovery did not make the universe feel chaotic. Strangely, it made the universe feel even more serene. Everything drifting, everything widening, everything part of a calm, continuous unfolding that began long before the first stars formed. And through this simple, elegant realization, the night sky changed. Not in appearance, but in meaning. The darkness overhead was no longer empty. It was deep, ancient, and slowly stretching. It held a story written in the soft glow of galaxies, a story that began with curiosity, unfolded with observation, and continues even now, moment by quiet moment, as space itself grows a little more. To understand what expansion truly means, it helps to begin with something simple. The universe does not behave like a collection of objects drifting apart through ordinary space. There is no great cosmic wind pushing galaxies away, no silent current carrying them outward like leaves floating on a river. The distances between galaxies increase, yes, but the galaxies themselves are not the ones making the journey. Instead, the space between them quietly grows. It is a subtle distinction, yet it transforms the way the cosmos is understood. Imagine holding a soft piece of fabric, something light and flexible, and gently stretching it. Any tiny marks on the surface move farther apart, yet they do not glide across the cloth. They stay exactly where they are. It is the fabric beneath them that changes. If the marks were small galaxies and the cloth was space, that motion would mirror what the universe does. Nothing races across the cosmos. Instead, the cosmos itself breathes outward. This idea can feel slippery at first, because the human mind is accustomed to thinking about motion as an object moving from one place to another. Every day is filled with simple, tangible examples: walking across a room, driving down a road, watching clouds drift past a window. But expansion is not that kind of movement. It is not something that can be pointed to or felt directly. Instead, Expansion is a change in the very meaning of distance. If one imagined the universe as a grand map, expansion would not move anything on that map. It would simply increase the scale printed along the edges. One of the most calming ways to picture this is to imagine small lanterns floating on a still lake at night. If the water beneath them began to rise and stretch in every direction, the lanterns would drift apart even though they remained perfectly still relative to the water around them. Expansion behaves in a similar way. Galaxies remain embedded in space, but space itself grows between them. And yet, this raises a soothing and surprisingly important question. If space is stretching everywhere, why is it not felt here? Why do everyday distances remain steady? The answer lies in the quiet interplay of forces, on small scales, within galaxies, within solar systems, within rooms and bodies and atoms. Gravity and other forces are strong enough to hold everything together. Expansion is unimaginably gentle when measured locally, so subtle that it cannot pry apart anything bound by even the faintest attraction. At the human scale, it is utterly invisible. Even within a galaxy, the gravity of billions of stars outweighs the influence of expansion completely. The galaxy's structure remains intact, its spirals held together as tightly as ever. Even entire clusters of galaxies resist stretching, their mutual gravity binding them into families that drift through the expanding universe together. Expansion only becomes noticeable when reaching for the immense distances between clusters, where gravity grows thin and space itself quietly takes the lead. Another helpful way to picture the behavior is to imagine a vast grid, an endless pattern of lines extending outward in all directions. Each crossing point is a galaxy, positioned calmly where the lines meet. As the universe expands, the grid stretches. The lines lengthen, but the galaxies remain at their intersections, unmoving in any ordinary sense. The pattern itself widens, carrying everything with it. This grid, though only an image, captures the essence of how the cosmos changes. Yet expansion is not identical to stretching a sheet of cloth or an elastic grid. Those images are merely stepping stones, not perfect mirrors. Real space is not pulled by hands, influenced by air, or resting within something larger. It expands on its own from within, without a surrounding environment to push against. There is no outside space into which the universe grows. It is better understood as a quiet change in the scale of the universe rather than a swelling into emptiness. This leads to another calming realization. Expansion does not imply movement with a preferred direction. There is no center from which everything flows outward. Every point in the universe experiences expansion in the same way. Observers in any galaxy would see other galaxies drifting away just as they appear to drift from ours. This uniformity is deeply peaceful in its own way, a reminder that no place in the universe is especially chosen or marked as the beginning point of cosmic growth. Of course, it is natural to wonder what exactly is stretching. How can something as intangible as space behave like an elastic medium? The truth is gently strange. Space is not a physical substance in the everyday sense. It does not stretch like rubber or fabric. Instead, it is a framework of relationships, a set of distances, angles, and connections that define how objects are arranged. Expansion simply means that those distances slowly increase. The fabric metaphor is helpful, yet the reality is more subtle, more mathematical, and ultimately more serene. Because the stretching of space is not like anything in daily life, it can help to use gentle comparisons without leaning too heavily on any single one. For instance, Imagine the surface of a balloon dotted with tiny ink specks. As the balloon inflates, the specks drift apart. This image captures the uniformity of expansion, the way every region grows without a central point. However, a balloon expands into air. Real space does not expand into anything. So the metaphor must be held lightly, like a description meant to point toward the truth rather than define it. Another image might be the rising of dough filled with grains of sugar. As the dough rises, the grains move apart, even though they do not push against each other. But unlike dough, space does not thicken or rise in a literal sense. Instead, the distances change in a way that is woven into the very rules of the universe. Expansion is gentle, smooth, and perfectly even when viewed on the scale of galaxies. In this quiet behavior lies one of the most beautiful truths of all. Expansion is not a violent explosion echoing from a single point. It is a calm unfolding that happens everywhere at once. The galaxies do not race outward from a central location. Rather, the universe itself widens, allowing every galaxy to drift from every other. This means there is no preferred direction in space, no special origin that sits at the center of everything. From any vantage point in the universe, the same gentle pattern emerges. It is also worth taking comfort in the fact that expansion does not threaten our place in the cosmos. It does not pull the Earth from the Sun or stretch the distances within the solar system. It does not lengthen the empty space between atoms or change the shapes of living things. All the familiar structures of daily life remain untouched, anchored by forces far stronger than the tiny influence of expansion on small scales. The universe grows, yet it allows the small islands of structure within it to remain peaceful, stable, and intact. What expansion truly offers is a broader perspective. It reveals that the universe is not fixed but gently evolving. It shows that everything once lay closer together, and that everything will drift farther apart in the long ages to come. This movement is not rushed or turbulent. It is a soft, continuous unfolding, a slow deepening of cosmic space that has been happening for almost 14 billion years. And so, to understand expansion is to understand a quiet rhythm that underlies the entire universe. Distances widen, light stretches, galaxies drift. Not because of a push or a pull, not because of motion in any ordinary sense, but because the structure of space itself changes. Expansion is a calm truth, a subtle feature of reality, and a reminder that the universe is far more fluid and serene than it first appears. In this gentle behavior lies the key to understanding the cosmos, a universe that grows everywhere at once, without hurry and without chaos, shaping the night sky one quiet moment at a time. In the earliest moments of the universe, everything was packed into a density far beyond anything the human mind is built to imagine. There was no emptiness, no quiet darkness, no gentle drift of distant galaxies. Instead, all the energy and matter that would one day form every star, every world, and every living thing was compressed into a state so hot, so crowded, and so intense that even the concept of space had not yet settled into anything familiar. It was a universe without room, without structure, and without the calm rhythms that fill the cosmos today. In that first fraction of a moment, the universe was unimaginably small and unimaginably hot. Not the heat of a star or the heat of molten rock, but a heat so fierce that particles could barely exist. Anything that formed was instantly torn apart. Everything flickered in and out of being, a restless sea of energy shifting so rapidly that stable forms were impossible. And yet, despite this chaotic beginning, something profoundly gentle was already underway. The universe was beginning to expand. This expansion in the early universe was unlike the slow, steady stretching seen today. In that primordial moment, the cosmos ballooned outward with astonishing speed. Distances increased faster than intuition would allow, carrying the universe from a tiny, compressed state into something with genuine size. As space grew, the intense heat began to soften. Cooling, in this case, did not mean a drop to comfortable temperatures. It simply meant shifting from unimaginable to merely extreme. Yet this slight change made all the difference. As the universe continued to expand and cool, conditions gradually reached a point where individual particles could endure for longer than a moment. Instead of flickering into existence and immediately dissolving, tiny building blocks could finally survive. Protons and neutrons took shape, forming the earliest hints of matter. These particles were not arranged into atoms or structures yet, but their stability marked a turning point. They were the seeds of everything that would one day exist. Still, this was no peaceful environment. The universe remained blisteringly hot, far hotter than the core of any star, and particles collided constantly. The density was so high that there was barely any space between them, and radiation flooded everything. Light could not travel freely. Instead, photons ricocheted endlessly, bouncing from particle to particle in a thick glowing fog. The early universe was not dark. It was brilliant, but in a way that no eye could see. It was a glowing haze, opaque and restless. During this time, when the cosmos was still young but noticeably larger than its earliest instant, simple forms of matter began to combine. Protons and neutrons linked together to form the first atomic nuclei. Hydrogen emerged first, then helium, and even a trace of lithium. It was a quiet act of cosmic chemistry taking place amid unimaginable heat. These nuclei floated in a sea of particles and light, waiting for the universe to cool enough to allow electrons to join them. For hundreds of thousands of years, the universe remained in this superheated state. Expansion continued steadily, stretching space and encouraging the temperature to fall. Yet it remained far too hot for atoms to assemble. Electrons were constantly plucked away from any nucleus they approached, leaving the universe filled with charged particles and trapped radiation. This period is sometimes described as the cosmic fog, because it behaved like a thick mist that refused to let light escape. And then, slowly and quietly, the universe crossed a threshold. After nearly 400,000 years of expansion and cooling, the temperature finally dipped low enough for electrons and nuclei to cling together. Hydrogen atoms formed in vast numbers, along with helium and the rare traces of other elements. With electrons now settled into orbit around nuclei, the universe changed in a profound and beautiful way. It became transparent. For the first time, light was free to travel. Photons that had been jostled and trapped for hundreds of thousands of years could finally move in straight lines. They streamed outward in all directions, filling the universe with a soft and ancient glow. These photons still exist, stretching gently as the universe expands, forming the delicate radiation known today as the cosmic microwave background. It is the oldest light the universe has to offer, a quiet message from an era when everything was simpler and more crowded. The transition from an opaque glowing fog to a transparent cosmos marked the true beginning of the universe, as it appears in the mind's eye. Space was still far denser than it is today, and temperatures remained hotter than the core of any present-day star. Yet the transformation allowed the first structures to begin forming. Tiny ripples in density, slight variations scattered throughout the early universe, became the seeds that would later grow into galaxies. Gravity, gentle but persistent, tugged on these ripples, encouraging matter to gather slowly in certain regions. The expansion that had begun in the earliest instant never stopped. Instead, it continued in a quieter, more measured way, giving the universe room to cool, room to gather, and room to evolve. Over millions of years, the once smooth sea of matter developed into patterns, clumps, and long filaments. The first stars ignited in these dense regions, their light shining across expanding space. Galaxies took shape, spinning slowly as gravity and inertia worked together. All of this, every star, every planet, every cluster of galaxies, came from the initial expansion and cooling that defined the universe's earliest moments. Without those first rapid changes in temperature and density, matter would never have had the chance to settle into stable forms. Light would never have been able to travel freely. The universe would not have gained the clarity and structure it needed to become a home for cosmic evolution. There is something deeply soothing about the arc of this story. The universe began not with stillness, but with heat and density so intense that nothing could survive for more than a moment. Yet expansion, gentle in spirit even when rapid in pace, created the conditions for calmness to emerge. Cooling followed naturally, as though the universe itself were taking a deep breath, softening from its earliest intensity into something broader and more open. The early universe's journey from blinding heat to clarity mirrors a transition from chaos to order, from impossibility to possibility. Everything that exists today, every star burning quietly in distant space, every swirling galaxy, every grain of dust, and every living thing traces its history back to this period when space was young, crowded, and unbearably hot. It is a reminder that even the most intense beginnings can soften with time. A universe that once held everything in a tiny blazing state now stretches gently towards spaciousness, allowing light to wander freely and matter to gather into shapes that endure across billions of years. And in that quiet transformation lies one of the most beautiful truths of all. Expansion did not merely happen at the beginning. It continues, moment by moment, carrying the universe from its crowded past into a future of ever-widening possibility. Across the vastness of the universe, galaxies appear to drift like quiet lanterns floating on an endless, darkened sea. Their motion is gentle, steady, and almost impossibly slow when measured on human timescales. Yet over millions and billions of years, the pattern becomes unmistakable. Nearly every galaxy beyond our immediate neighborhood appears to be moving away, as though the entire cosmos were slowly breathing outward. This drift is not a rush or a tumble. It is a smooth widening, a separation that unfolds with deep patience, shaping the universe in silent, persistent ways. To understand why galaxies appear to drift, it helps to picture them not as solitary wanderers, but as landmarks anchored in space. They do not swim through the cosmos like fish through water. Instead, the water itself expands and the landmarks move with it. The galaxies remain largely where they are, each one held together by its own gravity, but the distances between them grow. It is space that stretches, not the galaxies that roam. That single idea makes sense of the entire pattern. Our own galaxy, the Milky Way, sits within a small cluster of gravitationally bound neighbours. Andromeda, the Triangulum Galaxy, and several dozen smaller ones form a local family knitted together by mutual attraction. Within this small region, expansion has little influence. Gravity outweighs it completely. But once the view widens beyond this local cluster, expansion begins to show its quiet power. The gravitational pull between clusters weakens with immense distance, and space itself gently widens in those vast stretches between them. Over immense scales, this widening dominates, creating the appearance that distant galaxies are receding. It is easy to imagine that galaxies rushing away must be moving at incredible speeds, yet the truth is far more serene. Some galaxies do indeed move through space due to gravitational interactions, but the dominant effect responsible for their drift is the stretching of space itself. As space grows, light travelling across it stretches too. When this light reaches us, the stretching appears as a shift toward the red end of the spectrum. The greater the distance, the greater the shift. This redshift forms the quiet fingerprint of galaxies drifting apart. Imagine standing on a coastline as night settles in, holding a lantern and watching dozens more flicker far out across calm water. Each lantern glows steadily, barely shifting, barely changing. Yet if the water itself slowly rises and expands outward, those distant lights would drift farther from one another. They would feel as though they were gliding across the surface, though in truth, they remained fixed in place above the gently widening sea. That is the behaviour of galaxies on the grand scale. Within each galaxy, stars move in complex orbits, drifting through spirals or ellipses with speeds that can reach hundreds of kilometers per second. Despite this, the galaxy as a whole behaves as a single object. Its gravity holds it together firmly. Expansion cannot pry apart its stars, cannot stretch the space inside it, cannot unravel its spirals. A galaxy is too dense, too structured, too cohesive. Even galaxy clusters, some of the largest structures held together by gravity, remain intact. Though the universe expands, these clusters drift together through space like immense islands. The story is different once the distances grow large enough. Between clusters lies a kind of cosmic emptiness, regions where matter is sparse and gravity grows thin. In those places, expansion becomes the quiet ruler. The further apart two clusters are, the more space lies between them, and the more noticeable the expansion becomes. It is a gentle widening, like the slow spreading of the tide across a beach. This gentle drift paints the universe in a strange and beautiful way. Galaxies are not scattered arbitrarily, but arranged along vast filaments and sheets, forming a cosmic web. Between these structures are enormous voids where few galaxies live. Expansion gently widens these voids, stretching the distances between filaments, making the universe appear like an unfurling tapestry. Over billions of years the cosmic web remains, but the threads drift farther apart, smoothing the deepest structures of the universe into something larger and quieter. Understanding this drift also requires appreciating how still the universe appears from our point of view. If one could step outside at night and watch the galaxies themselves, their motion would not be visible. A human life is far too brief to witness even the smallest shift in their positions. The stars in the night sky remain fixed. The Milky Way's shape remains constant. Even Andromeda's slow approach, which will take place over billions of years, is invisible to the eye. The drift of galaxies is something revealed not through immediate sensation, but through patient measurement of their light. This subtlety is part of what makes the universe feel so calm. Its movement is not something that bursts forth or demands attention. It unfolds gradually, quietly, like the slow growth of a tree or the shifting of continents. On scales of human experience, everything appears steady. On cosmic scales, everything drifts. The widening of space also influences the way galaxies appear. Because light stretches as it travels, galaxies farther away seem different from galaxies nearby. Their colours shift, their shapes appear softer, their light grows dimmer. This creates a natural layering of the universe in time and distance. The galaxies closest to us show us the universe as it is now. The galaxies farther away show us the universe as it was long ago. Expansion is what allows this gentle layering. It is not just a physical behaviour, it is a kind of cosmic storytelling device, letting astronomers read the history of the universe by gazing outward. Interestingly, galaxies do not recede at the same rate everywhere. The drift increases with distance. A galaxy twice as far away drifts roughly twice as fast. This pattern emerges not because of the galaxies themselves, but because every stretch of space adds its contribution. The more stretches there are between two galaxies, the more expansion has time to accumulate. It is a calm, predictable behaviour, like watching ripples spread across a still lake, with each ripple pushing gently on the next. Even though galaxies drift apart, they do not lose their individuality. Galaxies continue to form stars, collide with neighbours, grow in size and evolve over time. Expansion does not dissolve them or pull them apart from within. It simply widens the backdrop on which they exist. It grants them more and more room as the ages pass. It is worth remembering that when astronomers look at faraway galaxies, they are seeing both space and time stretched together. A galaxy whose light has travelled billions of years shows us a version of the universe long gone, a younger cosmic era. Expansion allows that ancient light to arrive here, carrying its story across extraordinary intervals. And as time continues, this pattern deepens. The universe will keep widening, galaxies will drift farther apart, the cosmic web will stretch across ever-growing distances. Yet within each galaxy, life continues as though nothing were happening. Stars burn, planets circle, dust clouds whirl, and gravity holds everything together. Expansion may shape the largest structures in the universe, but the smaller, familiar islands of matter remain untouched. This chapter, then, is a quiet reflection on scale. To a galaxy, expansion is something that happens beyond its luminous arms, beyond the halo that surrounds it, far beyond the clusters to which it belongs. To the universe, expansion is a slow, steady motion that reshapes everything. These two perspectives coexist, just as calm shorelines coexist with the immense tides that gently rise and fall across the open sea. In this view, galaxies are not travellers moving with intention. They are lanterns drifting across a darkening ocean, carried by the widening surface beneath them. The drift is peaceful, patient, and built into the very structure of reality. And though the distances between them grow, each galaxy glows quietly on its own, a small island of light holding its shape within a universe that grows a little more every moment. When astronomers look out into the universe, they are not simply seeing distant objects. They are listening to light itself, using its delicate changes to understand how space grows, how galaxies drift, and how the cosmos has changed over billions of years. Light is not just illumination in this context. It is a messenger, carrying quiet clues from unimaginable distances. and in those quiet clues lies the evidence that the universe is gently expanding. One of the most important of these clues is something called redshift. When light travels across expanding space, its waves stretch. That stretching lengthens the wavelength, shifting it toward the red end of the spectrum. It is a soft change, a slow drifting of colour, but it reveals everything. The more the light is stretched, the farther it has travelled, and the more the space between us and the source has expanded. Astronomers measure this tiny shift and treat it like a cosmic fingerprint. It does not require touching a galaxy or feeling motion directly. The light alone is enough. To imagine this stretching, it helps to think of a sound you hear from far away, a long, low hum carried across a quiet field. As it travels, it softens and lengthens. Light does something similar as it crosses the growing universe. It leaves a galaxy in one colour, and by the time it arrives here, the colour has changed, pulled gently toward deeper reds by the expansion of the space it has passed through. This redshift is not random. When astronomers measure the light from many galaxies and compare their distances, a simple and elegant trend emerges. The farther a galaxy is, the more stretched its light becomes. That is the quiet signature of expansion. It shows that the deeper we look into the universe, the more space has grown while the light was travelling toward us. It is almost like looking at the rings of a tree, where each layer tells a story of time, except here the story is told by starlight. But how do astronomers know how far these galaxies are? The answer lies in another set of gentle clues: brightness and timing. Some stars, especially a type known as standard candles, behave in predictable ways. Certain stars brighten and dim with a rhythm so regular that their cycle acts like a natural clock. The timing of that brightness reveals their true power. By comparing how bright they appear from Earth to how bright they truly are, astronomers can estimate their distance. A star that seems faint but is known to be very luminous must be far away. This method creates a kind of cosmic ladder, allowing distances to be measured across greater and greater scales. These stars act as lighthouses scattered across the universe, each offering a clue about how far it stands from us. Once the distance is known, astronomers look at the colour of the light. If it is shifted toward the red, they calculate how much stretching has occurred. By pairing distance with redshift, they can chart how the universe itself has expanded over time. The measurements build a peaceful, predictable pattern, a widening cosmos revealed by the soft glow of very distant suns. Then there are clues that come from galaxies themselves. Large galaxies are made up of millions or trillions of stars, and their combined light can tell astronomers about their distance. Some galaxies have distinct features, like patterns in their spectra or relationships between their size and brightness, that serve as natural guides. These features allow astronomers to estimate distance even when individual stars cannot be seen. Everything in this process relies on patience. Light from the nearest galaxies takes millions of years to arrive. Light from the most distant galaxies may have travelled for more than 13 billion years. By the time that ancient light reaches Earth, the universe has changed dramatically from what it was when the photons first set out. This makes each photon a tiny time capsule. It carries a faint memory of the universe as it once was, a record of the conditions at the moment it began its journey. When astronomers capture these photons, they are not simply measuring colour, they are reading history. The cosmic microwave background offers one of the most powerful measurements of all. It is the soft echo of the early universe, a faint and ancient glow that fills the cosmos completely. Its temperature and smoothness reveal how space has stretched since the universe became transparent nearly 400,000 years after its birth. When astronomers study this background radiation, they see how the light has been stretched over billions of years, thinned and cooled by expansion. Today, it is just a whisper of warmth, hovering only a little above absolute zero. Yet that whisper is precisely what reveals the scale of the universe's growth. With all these clues layered together, redshift, brightness, timing, background radiation, astronomers build a picture of the universe that spans vast ages. None of the methods rely on direct contact. All depend on light that has wandered through space, carrying subtle imprints of distance, time, and expansion. Each photon is like a gentle traveller arriving from the far side of the cosmos, delivering its message with quiet precision. These measurements have shown that the universe is not simply expanding, it is expanding at an increasing rate. Distant galaxies drift away faster than closer ones, and extremely distant galaxies sometimes appear to be receding faster than the speed of light. This does not mean anything is breaking the rules. Instead, it means the space between us and those galaxies has expanded so much and continues to expand so quickly that the cumulative effect outpaces even light's steady speed. This behavior emerges naturally once the stretching of space is understood. If astronomers watch a single galaxy for a few years, they will not see movement. The changes are far too small to observe directly within a human lifetime. Yet by measuring the light from millions of galaxies at different distances, a gentle pattern emerges. That pattern does not rely on motion but on scale. It is not about how fast galaxies travel, but about how much space grows while their light is on its journey. This is why the universe feels both restless and calm. On the one hand, everything drifts apart. On the other, the drift is so slow from our perspective that it gives the impression of stillness. The measurements reveal the motion, but the night sky feels unchanged. It is a quiet cosmos, where the great changes happen over spans of time so long that no single human could ever witness them unfold. The beauty of these methods is that they turn the entire universe into a gentle laboratory. Every photon is a clue. Every distant glow is a measurement. Every faint redshift is a reminder that space is stretching all around us, all the time. None of this requires force or sound or sudden change. Expansion is revealed through patience, consistency, and a willingness to listen to light. In this way, astronomers do not just study galaxies, they study the quiet behavior of space itself. They trace the universe's history by observing how light has been stretched, dimmed, and shifted across billions of years. The cosmos leaves these clues everywhere, written in soft colours and faint signals. All that is required is careful attention. So the next time you imagine the universe expanding, think of the light that has travelled across it. Think of the photons that began their journey before the Earth existed, stretched along the way by the gentle growth of space. Think of the calm precision with which astronomers read these signals. It is through this patient listening that the story of an expanding universe is known, not through movement felt or seen instantly, but through the subtle imprints carried by the oldest travellers in the cosmos. Empty space sounds like a simple idea. It brings to mind a quiet void, a calm nothingness, a place where there is simply an absence of things. But in the universe, empty space is not quite empty. It has a personality of its own, a gentle behaviour woven into its very structure. Even in the quietest stretches between galaxies, regions with hardly a particle to find, space carries an energy that is subtle, smooth, and deeply important. This energy sits everywhere, in every direction, at every moment. It does not clump or gather. It does not swirl or flow. It simply exists, like a soft background note that never fades. The idea that nothingness could contain something seems contradictory at first. After all, emptiness is supposed to be the absence of everything. Yet when physicists study the fundamental nature of reality, they find that the vacuum is never truly bare. Tiny fluctuations flicker in and out of being, appearing briefly before vanishing again. Particles and antiparticles emerge from the quiet fabric of space for the smallest fractions of a second. The vacuum is never still. It seethes with potential, though that restlessness is impossible to sense directly. These fluctuations do not behave like ordinary energy. They have no light, no heat, no texture. They exist only as a whisper in the mathematics that describes the universe. And yet that whisper may influence the cosmos on the largest possible scale. Imagine standing in a vast open field on a windless day. The air feels perfectly calm. But deep in the atmosphere, unseen currents and tiny eddies of motion still drift through the sky. You cannot feel them, but they exist. Vacuum energy is similar. On the scale of atoms or even galaxies, it does nothing noticeable. But when stretched across billions of light years, its subtle presence becomes powerful. This quiet energy woven into space itself contributes to the way the universe expands. To visualize this, it helps to step back from thinking of space as a simple backdrop. Space is more like a dynamic fabric, something that can stretch, bend, and curve. When mass or energy is present, this fabric responds. It curves around stars and planets, creating the sensation of gravity. But it also responds to energy that fills space uniformly. Vacuum energy, even though subtle, exerts a kind of pressure. Unlike ordinary matter, which pulls through gravity, this smooth energy pushes. It does not push objects directly. Instead, it influences how space evolves, encouraging it to expand a little more with each passing moment. This push is not forceful or chaotic. It is uniform everywhere. It acts slowly, gently, and with perfect steadiness. It is almost as though empty space has a quiet preference for growing. This idea can feel abstract, so it may help to picture a soft, stretchy material laid out flat. Imagine that the material, even when untouched, slowly begins to expand because of a property woven into its fibers. Nothing pulls it outward, nothing pushes from the edges. It simply grows, not because of what lies on top of it, but because of what the material itself is made of. Space behaves similarly. It expands not because galaxies tug it apart, but because space itself contains a tiny but persistent energy that encourages it to stretch. This gentle stretching is not the same everywhere on smaller scales. Inside galaxies, gravity overwhelms the influence of vacuum energy entirely. The Milky Way does not grow. Planets do not drift from their orbits. Stars do not feel any outward pull. The tiny effect of vacuum energy is drowned out by the far stronger gravitational bonds holding matter together. But in the vast emptiness between galaxy clusters, where gravity is weak and matter is sparse, vacuum energy becomes noticeable. Across billions of light years, its cumulative influence creates the expansion we see today. The presence of energy in empty space also explains something curious about the universe's behavior. Expansion is not slowing down. At first glance, one might expect the gravity of all the matter in the cosmos to gradually pull everything back, slowing the drift between galaxies. For a long time, scientists believed this would happen, but when astronomers measured distant galaxies so far away their light has taken billions of years to reach us, they discovered something unexpected. Those galaxies were drifting away faster than expected. This meant the expansion of the universe was speeding up, not slowing down. This acceleration was one of the great surprises of modern astronomy. It implied that something in the universe was acting against gravity, not violently, not dramatically, but consistently. And the most elegant explanation was the energy hidden in empty space itself. When space expands, there is more space, and because vacuum energy is tied to the fabric of space, creating more space creates more of this quiet energy. The universe grows, and the energy that encourages growth grows with it. This creates a positive feedback loop. Not a runaway explosion, but a persistent, steady acceleration that gently shapes the universe's future. It is not that empty space becomes more energetic. The energy density of the vacuum stays the same everywhere. But as the universe expands, there is simply more of it, more volume, more fabric, more of that soft, uniform energy that encourages expansion. This behavior feels unlike anything in daily life because there is no close comparison. It is not like steam expanding or gas filling a room or heat spreading. Those processes rely on things moving into space. Vacuum energy is different. It is space. Its influence is a natural property of the cosmos, something that exists even when matter does not. This idea naturally leads to the concept of dark energy, a name given not because the energy is dark, but because it is mysterious. Dark energy may simply be another term for the energy of empty space, described in a more observational way. When astronomers measure the acceleration of expansion, they do not see the vacuum energy directly. They see its effect. They see galaxies drifting away more quickly. They see the cosmic web stretching faster in its widest spaces. They see the faint afterglow of the early universe slightly smoother than expected. All these clues point to something calm, uniform, and deeply embedded in space itself. If vacuum energy is indeed the source of dark energy, then the explanation becomes beautifully simple. Space expands because that is what it does when this energy is present. It does not require a mechanism or a push. It does not need something external to cause it. It is a gentle, intrinsic behavior of the universe. There is a peaceful quality to this idea. It suggests that the universe is shaped not only by dramatic forces like gravity and explosive events, but also by something quiet, constant, and almost invisible. In the same way that a soft background note can define the atmosphere of a room, the energy hidden in empty space defines the large-scale behavior of the cosmos. It is also a reminder that emptiness is not the absence of everything. It is a field of potential, a medium woven with subtle energy, a stage that influences the actors upon it. Even when stripped of all matter and light, space carries its own properties, and those properties guide the universe gently forward. The notion that space contains energy may be unfamiliar, but it is among the most comforting ideas in cosmology. It tells us that the universe does not require constant push or pull to evolve. It naturally unfolds, it naturally widens, it naturally takes its slow, patient steps into the future. And somewhere in that quiet expansion, in the invisible energy that fills even the emptiest regions, lies the key to understanding why the universe grows a little more with every passing moment. Dark energy is one of the most curious ideas in modern cosmology, not because it behaves dramatically, but because it behaves with such perfect subtlety. It does not shine, it does not cluster, It does not swirl into clouds or collapse into stars. It cannot be touched, collected, or isolated. And yet, whatever dark energy is, it shapes the entire universe. It gently influences the fabric of space, guiding its long-term evolution in a way that no ordinary substance can. In the quietest, calmest way imaginable, dark energy writes the future of the cosmos. To appreciate dark energy, it helps to begin with the simplest truth. It is a name for something we do not yet understand. It is not a substance we have detected directly. It is not a gas, or a field, or a type of matter in the familiar sense. It is not dark because it absorbs light, and it is not energy in the way a glowing filament or a warm ember contains energy. The word dark really means hidden, unseen, unmeasured, except through the gentle influence it has on space itself. What astronomers do know is this: space is expanding faster than expected. When they observe extremely distant galaxies whose light began its journey when the universe was young, they find that those galaxies are drifting away more quickly than gravity alone can explain. Something is counteracting gravity on the grandest scales, nudging space to expand a little more. This something behaves very differently from matter. It does not pull, it does not clump, it acts uniformly, everywhere at once, even where there is no matter at all. Whatever it is, this influence is called dark energy. One way to imagine dark energy is to picture a vast, calm lake. Ordinary matter behaves like stones or leaves floating on that lake. They drift, gather, collide, or sink. Dark energy behaves more like a quiet rising of the water level itself, a gentle lifting that affects everything equally, not because of the stones or leaves, but because the lake changes. Dark energy does not depend on where matter is located. It does not pay attention to galaxies or clusters or voids. It acts on space itself, encouraging it to widen. This makes dark energy fundamentally unlike the forces we know well. Gravity pulls objects toward one another. Electromagnetism creates the spark in lightning and the glow in lamps. Nuclear forces bind the centers of atoms. But dark energy is not about pulling or binding. It does the opposite. It softly encourages space to expand. Not explosively, not chaotically, just steadily, continuously, and with remarkable patience. The question of what dark energy actually is remains one of the deepest puzzles in physics. Some scientists propose that it might be the energy of empty space itself, a vacuum energy that fills every part of the universe. If this is true, then dark energy is not a separate ingredient added to the cosmos, but a property of space. In this view, every cubic meter of space contains the same tiny amount of energy, and as space expands, the total amount increases. This would naturally cause accelerated expansion, because creating more space creates more of this energy, which in turn produces more expansion. It is an elegant idea because it connects dark energy to the very structure of the universe. Others suggest that dark energy might be something more dynamic, a field that changes over time, perhaps stronger in some eras and weaker in others. This kind of field would ebb and flow as the universe evolves, subtly adjusting the pace of expansion. Some versions of this idea allow dark energy to slowly fade in the distant future. Others allow it to grow stronger. Some even imagine it transitioning into entirely new behaviors that the universe has not yet experienced. It is possible, too, that dark energy is not a substance at all, but simply a sign that our understanding of gravity needs refinement. Maybe gravity behaves differently over enormous distances. Perhaps the rules that work perfectly well within the solar system or within galaxies begin to shift when stretched across unimaginable expanses of space. If gravity weakens or changes behavior on those scales, the universe would appear to accelerate without requiring a new form of energy. At this stage, none of these explanations is confirmed, and far from being unsettling, this uncertainty adds a layer of quiet wonder to the universe. The cosmos continues to expand, and astronomers continue to measure its behavior with exquisite care, yet the underlying cause remains open. It is a reminder that scientific knowledge, even in its most advanced forms, contains gentle mysteries. Despite this uncertainty, dark energy plays a crucial role in shaping the future of the universe. Because it encourages expansion, it will influence how galaxies drift apart over trillions of years. As space widens, galaxies will slip farther from each other, and the light they emit will stretch into longer, gentler wavelengths. Over time, this drifting will leave isolated pockets of the universe surrounded by increasing darkness. Stars will continue to form for a time, but eventually the cosmos will become quieter, cooler, and more spacious. Dark energy guides this long arc, not with force, but with a whisper. This is why dark energy is sometimes described as a kind of cosmic pressure. It is not a pressure that pushes on objects, but one that emerges from the structure of space. Unlike ordinary pressure, which increases when particles move or collide, dark energy remains constant everywhere. It is the same in every direction, at every point, regardless of what the universe contains. Its uniformity is what makes it so effective at influencing the expansion of the universe. It acts like a gentle, even pulse woven into the fabric of reality. If dark energy had been stronger in the early universe, the cosmos might have expanded too quickly for galaxies to form. Stars might never have gathered. If it had been weaker, gravity might have drawn everything back together. Instead, dark energy has just the right subtlety to allow a universe filled with galaxies, stars, planets, and quiet pockets of life. Its presence allowed the cosmos to grow, not too fast, not too slow, but with a graceful balance that lets structures form before drifting apart. In this way, dark energy is not just a mystery, it is a quiet gift. It creates the long-term spaciousness of the universe. It shapes the gentle future that the cosmos is drifting toward. It ensures that the universe remains dynamic, ever-changing, ever-unfolding. And though no one yet knows exactly what dark energy is, its influence is one of the most precisely measured behaviors in all of cosmology. Every flicker of distant light, every subtle stretch of ancient photons, every widening of space tells the same story. Dark energy is there, calm and steady. There is a peacefulness to the idea that the universe contains something so subtle that it cannot be touched or seen directly, yet so powerful that it shapes the cosmos on the largest imaginable scale. Dark energy is a reminder that not everything important announces itself loudly. Some things act gently, so gently that their presence is known only through patience, observation, and the quiet willingness to listen to light that has travelled billions of years. In the end, dark energy remains a mystery not because science has failed, but because the universe is richer and more intricate than any single explanation. Its behavior hints at deeper truths still waiting to be discovered. Whether it is a natural property of space, a shifting field, a change in gravitational physics, or something entirely unforeseen, dark energy continues to guide the cosmos into its future with quiet assurance. And as the universe expands, so too does the invitation to understand it. Dark energy may be hidden, but its effects shine across the widest stretches of space, encouraging the cosmos to unfold moment by moment, patiently and peacefully, into the unknown. Gravity is one of the most familiar forces in the universe. It keeps your feet on the ground, holds the moon in its orbit, and gathers gas and dust into stars. It shaped the planets, carved the orbits of comets, and binds entire galaxies into elegant spirals. With such immense influence, it feels natural to wonder why gravity does not simply pull the universe back together. If everything attracts everything else, why does the cosmos not collapse inward? Why does space continue to widen, and why does gravity seem unable to stop that gentle unfolding? The answer lies in a quiet contrast. Gravity pulls on matter, but gravity does not shrink space itself. Matter responds to gravity, space responds to expansion, and once this difference is understood, the behavior of the universe becomes much clearer. Imagine a cluster of stars. Each star tugs on the others, pulling them inward, shaping the elegant whirl of a galaxy. Within that galaxy, gravity is powerful. Stars do not drift apart. The Milky Way does not unravel. Even as the universe expands, the galaxy remains intact because gravity binds it tightly. Expansion on small scales is far too gentle to change anything held together by gravity's steady pull. This is the first essential idea. Gravity dominates locally, in places where matter is dense, within solar systems, within galaxies, within clusters of galaxies. Gravity serves as the primary sculptor. It gathers, steadies, and binds. Expansion cannot pull apart the planets or loosen the orbit of the Earth around the Sun. It cannot stretch the distance between a star and its planets or weaken the structure of a galaxy. Gravity in these regions is simply stronger than the almost imperceptible pull of expansion. But the story changes as distances grow. Gravity weakens with distance, becoming fainter the farther apart two objects are. Between galaxies within a cluster, gravity still holds strong. But between clusters themselves, the distances become so immense that gravity's pull becomes almost non-existent. In those wide, quiet regions, the dark oceans between galaxy clusters, the influence of expansion becomes significant. Space stretches most easily where matter is sparse. To picture this, it may help to imagine a spider's web stretched across a garden. The silk threads represent gravity, holding the web structure together. If a small gust of wind blows, the web moves slightly but remains intact. Now imagine that the entire garden itself slowly expands. The plants drift a little farther apart and the web, connected between them, stretches gently with it. The web does not break. The silk threads resist small changes, keeping the pattern intact. But the wider the garden grows, the more the web is pulled outward overall. On the scale of galaxies, gravity is the silk thread. On the scale of clusters and beyond, expansion is the widening of the garden. The next important idea is that expansion is not a force acting on matter. It does not push galaxies apart like a gust of wind. Instead, expansion changes the meaning of distance itself. When space stretches, the distance between unbound objects grows, even if they never move through space. It is a geometric effect rather than a mechanical one. Because of this, gravity is not fighting expansion the way a weight fights a spring. They are not opposing forces. They are behaviors that take place on different scales and for different reasons. Gravity attempts to draw matter together. Expansion affects the grid of space between them. If two galaxies are not gravitationally connected, space can stretch freely between them, and gravity has no way to counteract that growth. It is not that gravity is too weak globally. but that gravity is simply not designed to act on the fabric of space itself. This creates a calm coexistence between the two behaviors. Gravity shapes the islands of structure within the universe, stars, planets, galaxies, and clusters. Expansion shapes the oceans between these islands, gradually widening the space in which those structures float. Some of the earliest observations that revealed this balance came from measuring the light of distant galaxies. When scientists compared the distances of galaxies with how much their light was stretched, they saw a beautiful pattern. Closer galaxies drifted away more slowly. Distant galaxies drifted away more quickly. This was not because distant galaxies were speeding away on their own, but because more expanding space lay between the observer and the distant galaxy. Gravity could not influence that entire region. The effect was cumulative. On these immense scales, expansion outpaces gravity simply because the space to be stretched is so vast. There is also a second layer to this story: dark energy, the subtle influence that encourages expansion itself. Dark energy behaves uniformly, filling every region of space with the same gentle pressure. In regions with little matter, such as the distances between galaxy clusters, dark energy's effect becomes more noticeable. Gravity cannot counteract it because there is no dense mass for gravity to draw together. While dark energy nudges the universe outward, gravity tugs inward only where matter is present. This gives the universe a quiet structure of balance. Gravity dominates where matter collects. Expansion dominates where emptiness rules. Neither wins outright because neither competes directly with the other. They simply operate in their own domains. To understand how gentle this behavior is, consider the following image. Picture a string of lanterns floating on a perfectly calm lake at dusk. If the water beneath them slowly widens, stretching in all directions, the lanterns drift farther apart. But the lanterns themselves remain whole and steady. They do not stretch. They do not distort. They simply appear to part ways as the surface beneath them grows. Gravity within each lantern holds it together, just as gravity within galaxies keeps stars bound tightly. Yet no lantern can stop the expansion of the lake, just as galaxies cannot stop the widening of space between clusters. Even though gravity cannot reverse expansion across cosmic distances, its influence is still profound. It shapes the quiet architecture of the universe. It gives form to galaxies and clusters, carves spirals and halos, and allows stars to burn. The expansion of the universe would be a very empty affair without gravity. Gravity creates the luminous islands that expansion gradually separates. This balance creates an interesting perspective on the universe's behavior. On small scales, gravity appears overwhelmingly strong. It binds matter into orbits and structures that last for billions of years. On large scales, expansion appears effortlessly dominant, shaping the future of cosmic distances. Neither perspective is incorrect. Both are true, depending on the scale being examined. This scale-based behavior leads to a final, gentle realization. The universe is not a place where gravity must lose to expansion. It is a place where gravity and expansion form two parts of a larger whole. Gravity sculpts, expansion opens, gravity gathers, expansion spreads. Together they create a cosmos filled with both structure and space, both closeness and distance. The future of the universe will be shaped by this relationship. Galaxies will remain intact, each one a glowing island held together by gravity's patient pull. But the distances between those islands will continue to widen. Over the course of unimaginable time, galaxy clusters will drift farther and farther apart, disappearing beyond cosmic horizons. gravity will continue to hold its small domains, while expansion governs the immense distances between them. And so, gravity does not fail to pull the universe back together. It simply works where it is meant to work. It binds stars, shapes galaxies, and anchors clusters. Expansion works on the vastness between those clusters. The universe is not a battlefield between opposing forces, but a calm coexistence between two behaviors that unfold across different scales. Seen this way, the cosmos becomes a serene landscape. Islands of light drift apart on an ever-widening ocean of space, each island perfectly intact, each one glowing quietly. Gravity ensures the lanterns burn steadily. Expansion ensures the sea grows gently. Together, they create a universe that is open, balanced, and quietly evolving, moment by moment, as space continues its slow, patient widening. When we talk about the universe expanding, drifting, stretching, and widening in every direction, it raises a gentle but important question. What exactly is it expanding into? And if it is growing, what shape does it have? Does it curve? Does it bend? Is the universe flat like an endless sheet, curved like the surface of a balloon, or shaped in some way that does not resemble anything familiar? To understand cosmic curvature, it helps to set aside everyday intuitions. The shapes we know best, lines, circles, spheres, live comfortably in three-dimensional space. But the shape of the universe is not a physical object floating inside something larger. It is the shape of space itself. And because space is the stage on which everything exists, its shape must be described without imagining an outside. This makes curvature feel abstract at first, but with the right imagery it becomes surprisingly intuitive. Curvature, in the cosmological sense, describes how space behaves when you move through it. In a perfectly flat universe, if you travel in a straight line, your path never bends inward or outward. Angles add up exactly as expected. Parallel lines remain parallel forever. This kind of space feels familiar because the geometry of ordinary life behaves this way. A flat universe is spatially simple, stretching outward evenly and endlessly. A curved universe behaves differently. If space has positive curvature, like the surface of a sphere, straight lines eventually come together. Imagine drawing two lines on a globe that start at the equator pointing north. They begin parallel, but as they approach the pole they converge. Distances and angles behave differently. If the universe were positively curved, travelling far enough in a straight line might eventually bring you back to where you began, although the distances involved would be so enormous that such a journey would be purely hypothetical. On the other hand, a universe with negative curvature resembles a saddle shape. Straight lines bend away from each other, distances behave in unfamiliar ways, and the geometry feels subtly stretched. If space had negative curvature, the universe would expand differently, and the distribution of galaxies across the sky would carry that signature. These images help because they capture something essential. Curvature is not about the universe being a physical object sitting inside a larger space. It is about how distances behave within the universe itself. To get comfortable with the idea, imagine a perfectly flat sheet of paper. Now imagine that same sheet bent into a gentle arc. The paper is still two-dimensional, but it curves through three-dimensional space. The key point is not the bending itself, but how shapes drawn on the sheet behave. If you draw a triangle on a flat sheet, the angles add up to 180 degrees. If you draw a triangle on a curved surface, the angles add up to more or less. The change in angles reveals the curvature. Astronomers cannot step outside the universe to see its shape. They cannot look at it from above or from the side, but they can measure its curvature by looking at the angles of extremely distant patterns. The oldest light in the universe, the gentle glow of the cosmic microwave background, contains ripples, small fluctuations in temperature scattered across the sky. These ripples have a characteristic size. If the universe is flat, they appear at one size. If the universe curves inward or outward, that size shifts. When astronomers measured these ripples, they found something remarkable. The angles matched perfectly with a flat geometry, not slightly curved, not noticeably bent, flat as could be measured across the observable universe. This does not mean the universe is absolutely and perfectly flat in every possible sense, but it does mean that on scales stretching across tens of billions of light years, space behaves as though it has no overall curvature. If there is any curvature at all, it is extremely subtle, so gentle that even the oldest light has not revealed it. This flatness carries deep meaning. A flat universe feels infinite in extent, at least within the limits of what can be observed. It stretches outward without edges or boundaries. Its geometry is familiar. Its behavior is steady. And expansion unfolds smoothly along this subtle fabric. The shape of the universe also influences its fate. A positively curved universe, if dominated by gravity, might one day contract. A negatively curved universe might expand forever in a dramatically thinning way. But a flat universe sits on the balance point between these two behaviors. Its expansion depends on the energies contained within it. Matter, radiation, dark energy, but not on curvature itself. Because the universe appears flat, the story of its expansion is guided more by what fills space than by the shape of space. A gentle metaphor for curvature is to imagine walking across an enormous meadow. If the ground is completely flat, your steps feel even and predictable. If the ground is slightly curved upward, walking feels subtly different, even if the curvature is too slight to notice with the eye. The universe behaves like that meadow. Galaxies follow paths shaped by the geometry beneath them. Light travels along routes shaped by the curvature of space. If space is flat, light moves exactly as expected. If space is curved, the paths bend in subtle ways, altering how distant objects appear. Interestingly, local curvature caused by mass, is very different from global curvature. When a planet curves space around it, that is a local effect. It shapes orbits, influences light, and bends trajectories. But when cosmologists talk about curvature in this chapter, they mean something broader. Whether the entire universe has an overall curvature on the largest imaginable scales. Despite the local curvature of stars and galaxies, the universe as a whole appears almost perfectly flat. This has consequences for how galaxies are arranged. A flat universe produces a large-scale structure, the cosmic web, that spreads evenly across space. Filaments of galaxies stretch outward in long, elegant lines. Clusters form at the intersections. Voids open up between the threads. A curved universe would influence how these patterns formed and how they spread. The near flatness observed suggests that the cosmic web grew within a gentle, balanced geometry. The idea that the universe might be flat also fits comfortably with the behavior of expansion. In a flat universe with dark energy guiding the expansion, the cosmos widens calmly, slowly accelerating over time. Distances grow, galaxies drift farther apart. But the universe does not fold back on itself, nor does it thin into something unreasonably stretched. It grows with a quiet steadiness, shaped by a subtle geometry that does not distort the large-scale structure. A helpful image for this is to picture the universe as a vast, gently woven fabric stretched across a frame. The fabric is smooth. It does not bulge upward or sink inward. It holds its form as it expands, remaining even and level across its entire extent. That smoothness is what cosmologists see when they measure the cosmic microwave background. Its ripples are evenly sized. Its patterns are symmetrical. The light behaves exactly as it would in a flat universe. The shape of the universe is not just a technical detail. It is part of its personality. A curved universe feels enclosed or dramatically stretched. A flat universe feels open and steady. In a sense, it creates the backdrop against which cosmic history unfolds. A flat universe gives space a calm and gentle consistency, a quiet canvas on which galaxies form, drift, interact, and glow. There is a quiet beauty in the fact that space is nearly flat. It means that the universe is vast and open. It means that light travels with gentle predictability. It means that expansion is smooth, not distorted by curvature. And it means that the cosmos holds a sense of balance that is both mathematically elegant and emotionally soothing. So when you picture the universe expanding, imagine it doing so across an almost perfectly flat landscape, one that stretches evenly in every direction, one without edges, one without boundaries, one that quietly supports the drifting lanterns of galaxies. The curvature of space, so gentle and subtle, helps shape the entire cosmic story. And in its serene, nearly flat geometry, the universe reveals one more layer of its calm and quietly beautiful nature. There is a gentle strangeness to the universe that becomes clearer the farther out we look. On human scales, nothing ever moves faster than light. A beam from a torch or a distant star races at the ultimate speed limit, a speed nothing else can outrun. Yet across the vastness of the cosmos, some distant galaxies drift away from us faster than that limit. Their light stretches into longer and gentler wavelengths, fading into colours the eye cannot see. Eventually their glow slips beyond even the reach of telescopes, and though they still exist, still shining, still spinning, still drifting, they become unreachable forever. This idea sounds impossible at first, as though nature were contradicting itself. How can something move faster than light without breaking physics? How can a galaxy recede at a speed that no object is allowed to achieve? The answer lies in a simple, peaceful truth. Those galaxies are not moving through space faster than light. The space between us and them is expanding. The road, not the traveller, is lengthening. And because the universe can stretch without limit, the distance between 2 points can increase faster than any object could travel across it. This is the heart of cosmic horizons, the quiet boundaries drawn not by walls or edges, but by the behaviour of space itself. To imagine this, picture yourself standing on a shoreline at dusk. A lantern floats on a calm lake just within view. As the water slowly expands outward, as if the surface itself were stretching, the lantern drifts away even though it does not paddle or push. If the water stretches quickly enough, the lantern will drift so far that the light it sends out will never reach you. Not because the lantern refused to shine, but because the surface between you and it expanded too quickly for the light to make the crossing. The universe behaves in much the same way. Light always travels at the same speed. That rule is never broken. but the distance light has to cross can expand faster than the light can move forward. When that happens, the light is carried away with the growing space, like a swimmer trying to cross a river that widens faster than they can move. They stroke forward endlessly, yet the far bank retreats even faster. This gentle behavior creates the idea of a cosmic horizon, a place beyond which events can never influence us, no matter how much time passes. The horizon is not a physical barrier. Nothing marks it. Nothing signals its presence. It is simply the distance at which space expands faster than light can travel through it. Anything beyond that point becomes permanently out of reach. Even if a galaxy beyond the horizon shines with brilliant light, that light will never arrive. It will be stretched and carried outward endlessly, caught in the same expansion that creates the horizon in the first place. From our perspective, such galaxies slowly fade. Their light drifts into longer wavelengths, shifting through red, then through infrared, then into wavelengths so long and subtle that no telescope can detect them. Eventually they disappear from view entirely, not because they have vanished, but because the universe has expanded too much for their light to find us. This does not mean the cosmos is shrinking from our perception. Instead, it means the universe is so large and so dynamic that parts of it drift beyond our ability to explore. Horizons remind us that the universe is not merely big, it is also evolving. It widens with every passing moment, and in doing so it creates boundaries that change with time. There are two main kinds of horizons to imagine gently. One is the horizon of what we can see right now, the distance from which light has had enough time to reach us since the universe began. Beyond that distance lies a region filled with galaxies that have not yet had the chance to show themselves to us. Their light is still on its journey, crossing expanding space. Some of that light will reach us eventually, bringing ancient messages from places we can only imagine today. The other horizon is more mysterious, the limit beyond which even future light will never arrive. This is the true cosmic horizon. It marks the edge of our potential view and our potential influence. Galaxies beyond that horizon are not simply too far away for now, they are too far away forever. As the universe continues to expand and the pace of that expansion subtly increases, more and more galaxies drift beyond this boundary. This does not make the universe lonely, it makes it wondrous. Imagine how extraordinary it is that we can see as far as we do, that we can catch photons that began their travels billions of years ago. These ancient messengers cross unimaginable distances, passing through the quiet wilderness between galaxies, arriving here as faint reminders of faraway light. Yet even their journeys have limits. Expansion gently stretches their paths and, in doing so, defines the edges of what we will ever see. The emotional weight of cosmic horizons is subtle. There is a softness to the realization that some places will forever remain hidden. It is not a harsh boundary, not a locked door or a forbidden region. It is simply a natural consequence of living in a universe that stretches as it evolves. Even if we had perfect spacecraft capable of traveling near the speed of light, horizons would still exist. No amount of determination or ingenuity could cross them, because the boundary is created not by speed, but by the behavior of space itself. This creates a peaceful sense of scale. The universe is not something to be traversed in a single journey. It contains regions so distant that they drift away faster than any spaceship, any photon, any message can travel. And yet the parts of the universe that remain within our horizon form a rich, intricate tapestry. galaxies, stars, clusters, and filaments woven together with gravity and light. These reachable regions contain everything we will ever observe, everything we will ever measure, and everything we will ever learn from directly. Horizons also give shape to time. When you look at the sky, you're not seeing the universe as it is, but as it was. Some galaxies appear as they existed billions of years ago, because the light has taken so long to reach us. Horizons add an extra layer to this, showing not only where the past becomes visible, but where visibility ends entirely. They represent both the universe's generosity, allowing us to see so far, and its quiet limitation, keeping some places forever beyond view. There is something deeply poetic about that balance. The universe lets us look back almost to its earliest moments, yet also reminds us that some corners will always remain unseen. It offers vast knowledge, but not infinite access. It invites exploration, but not complete understanding. In this way, horizons add a kind of humility to cosmology. They remind us that even the most powerful telescopes can only reveal a fraction of what exists. As the universe continues to expand in future ages, horizons will shift. More galaxies will drift beyond reach. The sky will slowly lose its most distant lanterns. The cosmic ocean will darken at its far edges, leaving only the closest islands of light visible. Yet this slow separation is not frightening. It is simply the universe's quiet way of growing, opening wider even as parts of it drift beyond the light we can catch. So when you imagine horizons, think of them not as walls, but as the soft, fading edge of what the universe allows us to see. Think of distant galaxies slipping gently beyond the reach of light, not because they are escaping, but because space itself is stretching beneath them. Think of horizons as the serene boundaries of a cosmic landscape, too vast to cross fully. And remember that within these boundaries lies a universe already filled with beauty, immeasurably deep, endlessly intricate, and steadily drifting outward into the unknown. In the deep future of the universe, long after the present moment has faded into memory, the cosmos will settle into a quieter, more spacious state. The expansion that gently separates galaxies today will continue, stretching the fabric of space with slow persistence. This widening will not be dramatic or turbulent. Instead, it will unfold with the same calm rhythm that shapes the universe now, a steady drift that carries galaxies into ever deeper isolation. To picture this future, imagine the night sky as it appears now, filled with distant galaxies, glowing softly through the darkness. The light from those galaxies has travelled for millions or billions of years to reach us. Some of the faintest smudges of light visible through modern telescopes were emitted when the universe was incredibly young. These distant galaxies form the backdrop of the cosmic picture we know today. As time stretches onward, that backdrop will slowly fade. The galaxies farthest from us will drift beyond the cosmic horizon, carried away by the accelerating expansion of space. Their light, already stretched into long, gentle wavelengths, will eventually slip beyond visibility. Even the most powerful telescopes will no longer be able to capture their glow. They will not vanish in any violent sense. Rather, they will fade like lanterns drifting beyond the edge of a widening lake, their light simply unable to bridge the growing distance. Over billions of years, the night sky will grow emptier. The great cosmic web, once filled with luminous clusters and filaments of galaxies, will thin out from our vantage point. Only the galaxies bound tightly to us by gravity will remain visible. In our own region of space, the Milky Way and the Andromeda Galaxy will merge into a single, large, smooth galaxy, often called Milkdromeda, surrounded by smaller companions drawn into its gravitational well. This new galaxy will glow quietly, drifting through an increasingly lonely region of the universe. Beyond this local family, however, the rest of the cosmos will slip further away, leaving behind vast stretches of darkness where galaxies once shone. The universe will not become empty, only our reach into it will shrink. The distant galaxies will continue to exist in their own regions of space, forming stars and evolving in ways we will never witness. But their light will no longer travel fast enough to overcome the ever-widening distances. This slow fading of the universe shapes the nature of cosmic time. In the far future, the story of the universe will no longer be written across countless galaxies. It will be written within a small group of gravitationally bound systems. Astronomers living in that distant era, if any exist, would see a sky unlike the one we know. They might believe their galaxy is the only one in existence, with the darkness beyond offering no clues that the universe was once filled with thousands of billions of glowing islands. Yet even in this quieter future, change will continue. Stars within the merged Milkdromeda galaxy will live their long lives, shining for trillions of years. New stars will be born for a time, formed from the remnants of older ones. But star formation will eventually slow as the galaxy uses up its available gas. The bright spirals of the present-day universe will give way to a calmer, more uniform glow of long-lived stars drifting through wide, dark regions of space. As time stretches onward, the universe will cool, starlight will thin, energy will spread out over larger and larger volumes of space. This cooling is not a rapid freeze, but a soft, gradual decline, like the fading warmth of a summer evening. Over unimaginable spans of time, even the longest-lived stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. These remnants will drift through the dark, glowing faintly at first, then cooling into stillness. Expansion will continue through all of this. The distances between surviving structures will grow so large that communication, even at the speed of light, will become impossible. If intelligent beings exist in that era, they will live in a quiet cosmic island surrounded by darkness, unaware of the grand history that preceded them unless ancient records survive to tell the tale. After even longer stretches of time, the story becomes gentler still. The universe enters ages so vast they defy normal comprehension. Black holes slowly evaporate through a process that unfolds over mind-bending intervals. The last traces of starlight fade. The last pockets of warmth spread out until they are indistinguishable from the empty background. Expansion will not stop. It will continue widening the universe, diluting its energy and smoothing its texture. This deep future might sound desolate at first glance, like a universe drifting towards silence. But there is another perspective, one that finds beauty in the scale and patience of cosmic time. The universe is not disappearing, it is maturing. It is following a natural trajectory shaped by its initial conditions and the subtle influence of dark energy. Just as living beings move from moments of brilliant energy to quieter phases, the universe follows its own arc, from crowded beginnings to peaceful openness. And throughout this long journey, expansion remains a quiet companion. It never rushes, it never shakes, or fractures the structures it passes. It simply widens the distances between them, creating more room, more stillness, more of the spacious darkness that characterizes the universe's later years. If one imagines drifting through that distant future, the experience would feel strangely serene. A single, massive galaxy glows softly within an ocean of darkness, its stars slowly aging, its remnants drifting through calm space. Beyond it lies endless night, deep, quiet, and profoundly still. It is a universe in a meditative state, no longer bursting with new light but resting after an eternity of motion. And yet even in that stillness, the story of expansion continues. The universe remains dynamic in its own subtle way, breathing outward as it always has. The galaxies might be gone from view, but the widening of space is eternal, patient, and gentle. It is a reminder that cosmic time is not measured in human lifetimes, or even in the rise and fall of galaxies. It is measured in the long, slow unfolding of space itself. Expansion carries the universe forward, shaping both its vibrant youth and its tranquil old age. And in the deepest future of all, the universe will still be expanding, quietly, steadily, endlessly, long after every star has faded from view. In that sense, the deep future of the universe is not bleak. It is spacious. It is calm. It is the natural continuation of a cosmos that has grown from a hot, crowded beginning into a wide, serene expanse. And even when the night sky grows empty, the memory of its brightness will remain, carried in the gentle story of a universe that spent its entire existence drifting toward openness. There is a quiet curiosity that sits beneath every conversation about the expanding universe. Will it always expand? Could the widening of space ever ease, pause, or even reverse itself? These questions drift through cosmology like soft echoes, not because scientists expect sudden changes, but because the universe has a long history of surprising us. In the spirit of calm exploration, it is worth imagining these possibilities gently, following them through without urgency, and seeing what they reveal about the cosmos. To begin, it helps to recognize that expansion is not driven by motion alone. It is shaped by the ingredients of the universe: matter, radiation, dark matter, and especially dark energy. How these ingredients behave over time determines whether the universe continues stretching or eventually slows. In the present era, dark energy plays the leading role. Its gentle, uniform influence encourages expansion to accelerate rather than fade. Yet because the true nature of dark energy remains unknown, there is room for careful imagination. Perhaps dark energy could change. Perhaps it might fade. Perhaps it might reverse its influence entirely. These possibilities are not predictions, but thoughtful explorations of what the laws of nature could, in principle, allow. One scenario to consider is the simplest. Dark energy may weaken over time. If it behaves as a field rather than a fixed property of space, it could gradually lose strength. In that case, the outward push supporting acceleration would soften. Expansion might slow. The universe would continue growing, but at a gentler pace, no longer racing apart as quickly as before. Galaxies would still drift away from one another, but the widening might eventually settle into a slow, steady stretch, rather than a continuously increasing one. Another possibility is that dark energy could fade completely. If it were to diminish to zero, the universe would be left with gravity and the momentum of its earlier expansion. Gravity, acting over huge distances, could begin to assert a quiet influence again. It would not pull galaxies back immediately, but over long times it could decelerate the expansion. The universe might grow more slowly, perhaps approaching a state where expansion continues forever but never accelerates again. This future would resemble a gentle coasting, with galaxies drifting apart but without the increasing pace that characterizes the present era. A more dramatic idea imagines dark energy not just fading, but changing sign. If its influence were to flip from a gentle push to a soft pull, the universe could begin to contract. Expansion would slow, then pause, then reverse. Galaxies that once drifted away from each other would begin moving closer. Over even longer times, the universe could shrink in size, growing denser and warmer as matter was drawn inward. This hypothetical future is sometimes called the Big Crunch, a reversal of the cosmic unfolding that brought the universe from a hot, crowded beginning into the wide, open spaces it occupies today. In this scenario, the cosmos would gradually tighten its shape. Distances would shorten, heat would build. The universe could eventually collapse into a state reminiscent of its earliest moments. Whether such a collapse would mirror the universe's original beginning or lead into some new phase is a deep and open question. The idea is not frightening when viewed through the enormous lens of cosmic time. If it were ever to happen, it would unfold over spans of time so immense that even the longest-lived stars would have burned out long before any meaningful contraction began. There are gentler variations of this imagined reversal. Some theories propose that the universe might transition through cycles, expanding, slowing, collapsing, and expanding again in a rhythmic pattern. Each cycle could have its own character, its own structure, its own story. These ideas are speculative, but they offer a poetic sense of cosmic rhythm, as though the universe breathes in great pulses spanning trillions of years. However, despite the beauty of these possibilities, the current evidence suggests a quieter, more straightforward future. Everything astronomers observe points toward continued expansion. The light from distant galaxies shows a consistent pattern of acceleration. The behavior of the cosmic microwave background aligns with an expanding universe driven by a persistent form of dark energy. And the measurements of galaxy clustering, gravitational lensing, and supernova brightness all tell the same story. Dark energy appears uniform and steady. If dark energy remains constant, the universe will continue to expand indefinitely, not just for billions of years, but for trillions of trillions. The widening will accelerate gently. Galaxies will drift apart. The cosmic horizon will grow, placing more and more of the universe beyond reach. This future is not dramatic. It is not explosive. It is a long, slow unfolding, almost meditative in its pace. Yet even within the calmness of this expected future lies uncertainty. Scientists do not yet know exactly what dark energy is. They do not know whether it is an unchanging property of space or something dynamic that evolves over time. They study it through the faintest stretches of ancient light, comparing distances and brightness across billions of years. They test ideas with careful patience, knowing that the true nature of dark energy may reveal itself slowly, like a quiet pattern emerging from distant starlight. This uncertainty does not bring tension. It brings openness, a sense that the universe may still hold surprises. The cosmos is not rigid or fixed. It is a place of change, a place of deep time, a place where even the largest structures evolve in ways the human mind can barely grasp. Considering alternate futures allows the imagination to stretch gently, just as space stretches across unimaginable distances. It is also comforting to realize that any change in expansion, whether slowing or reversing, would unfold on timescales vastly longer than the entire history of life on Earth. The universe is enormous not just in space but in time. Its rhythms are measured in intervals far beyond ordinary experience, And in that perspective, the future becomes something spacious, something soft, something that cannot be rushed. So could expansion slow, pause, or reverse? The answer is a calm perhaps. The universe contains the ingredients for many possible futures, and without a complete understanding of dark energy, the door to alternate cosmic fates remains gently open. But the best evidence available points toward continued expansion, a future in which the cosmos grows more spacious with every passing moment. This does not diminish the beauty of the alternate possibilities. They serve as quiet reminders that the universe is not bound to a single path. They invite reflection on the nature of time, the flow of cosmic history, and the subtle forces that guide the universe. Whether expansion continues forever or one day changes course, the cosmos remains a place of wonder, vast, evolving, and filled with mysteries waiting to be uncovered through patient, gentle understanding. And for now, the universe continues its slow, steady widening, drifting outward into the darkness with quiet grace, moment by moment, as it has for billions of years. Across many cultures and eras, humans have found comfort in the idea of cycles. Seasons turn, tides return, hearts beat, and days rise and fall in an endless rhythm. There is something deeply soothing about patterns that do not end, movements that return to where they began, stories that renew themselves again and again. It is perhaps no surprise, then, that some cosmological theories explore the possibility that the entire universe might behave this way. Not as a single unfolding story from beginning to end, but as part of a grand sequence of cycles stretching across unimaginable spans of time. In these ideas, the universe does not simply expand forever. Instead, it breathes. It widens, pauses, contracts, and then begins again. Each cycle may differ slightly from the one before, much like the subtle variations between seasons, or the quiet differences between waves returning to a shore. These cosmic rhythms, though entirely speculative, offer a perspective that is both scientifically intriguing and emotionally resonant. They present the universe not as a one-time event, but as a continuing dance of creation and renewal. To imagine a cyclic universe, it helps to step into its rhythm gently. Picture the universe expanding for trillions of years, growing vast and open, galaxies drifting farther apart until the night sky is almost empty. At some point, far beyond any time we can meaningfully grasp, the expansion slows. Perhaps the energy driving expansion weakens. Perhaps gravity becomes just strong enough to counteract the widening. Perhaps some new behavior emerges from the deep structure of reality. Whatever the cause, space stops stretching. It becomes still. Then, quietly at first, contraction begins. Distances shrink. Galaxies that had once drifted away from each other begin to move closer again. Over yet more unimaginable intervals, the universe slowly collapses, gathering its matter and energy into a smaller and smaller region. The cosmos warms as it contracts, the same way air grows warmer when compressed. Galaxies merge, stars collide. The temperature of the universe rises until it becomes a dense, hot, crowded place once again. Eventually, in this picture, the cosmos reaches a point where a new beginning becomes possible, a new expansion, a new cycle, a new cosmic era. This rhythmic view of the universe is not meant to be dramatic. Instead, it is meditative. Each cycle stretches across spans of time so immense that even entire galaxies live and die as brief flickers within the larger rhythm. Every cosmic era contains its own story, its own stars, its own potential for planets, life, and meaning. And long after those stories end, the universe begins anew. There are several scientific ideas that propose these cosmic rhythms, each offering a slightly different interpretation. Some models suggest that the universe bounces, a contraction phase followed by a rebound, creating another expansion. Others propose that space does not collapse into a single point, but transitions smoothly into the next cycle through a subtle transformation of geometry. A few models imagine cycles not of the whole universe, but of the fabric of space-time itself, patterns of behavior that repeat even if the physical contents of the universe do not. One of the gentle appeals of these theories is that they offer an alternative to a universe that simply expands into even greater emptiness forever. Rather than drifting endlessly into a colder, quieter state, the universe in these models lives through grand epochs, each one renewing the cosmos with fresh possibilities. It is a view that resonates with many philosophies. The idea that nature moves in patterns, that endings are transitions, and that time is more circular than linear. Of course, these rhythmic models remain speculative. They require assumptions about the behavior of dark energy, about the nature of gravity at extreme scales, and about how matter behaves under extraordinary compression. Many of the ideas rely on mathematical frameworks that are elegant but untested. Some would require new physics entirely, effects that do not appear in present-day experiments or observations. Yet this uncertainty does not diminish their beauty. The speculative nature of cyclic universes gives them a dreamlike quality, allowing the imagination to wander through cosmic scenarios that blend science with quiet wonder. It is not necessary to believe that these cycles are real in order to appreciate their conceptual grace. They offer a broadening of perspective, an invitation to consider the universe not as a single event, but as a sequence of eras, each one rising from the remnants of the last. In some cyclic models, each successive universe inherits subtle traces from the previous one, faint patterns or imprints that survive the transition between cycles. These imprints might influence the distribution of galaxies, the shape of cosmic fluctuations, or the early behavior of expansion. If such traces exist, they would act like the faint echoes of ancient cosmic rhythms whispering through the present universe. Other models imagine the cycles as entirely separate, with no memory carried over. In these ideas, each universe begins without reference to any that came before it. The cycles are connected only by the flow of time, not by shared structure. This view is more like a cosmic symphony, where each movement rises and falls independently, but together they create an infinite composition. What makes these concepts emotionally powerful is not their predictive certainty, but their philosophical resonance. They allow the universe to be imagined as something living through vast seasons, springs of creation, summers of stability, autumns of fading light, and winters before renewal. These seasons take place over spans far beyond the existence of stars or galaxies, yet they share the same quiet rhythm that makes cycles comforting. Even if the universe is not cyclic in any literal way, the idea gently broadens the imagination. It reminds us that the cosmos could behave in ways very different from immediate appearances. Expansion could be part of a longer pattern. The story of the universe might not be a straight line pointing toward a single fate, but a looping curve, returning in unexpected ways. At the very least, the possibility invites curiosity and humility, two qualities that help make cosmology such a peaceful field of study. It is also worth remembering that the universe has already moved through different phases. It began in a hot, dense era, cooled into a period of star and galaxy formation, shifted into an age dominated by expansion, and will drift into future ages that differ yet again. In a sense, even without true cycles, the universe has its own soft rhythms, patterns of growth, change and transition that stretch across its long life. In the end, the idea of a cyclic universe is an invitation rather than a conclusion. It invites the mind to imagine a cosmos not limited to a single beginning or a single ending. It invites reflection on the patterns that might lie beyond current knowledge. It offers a sense of continuity in a universe that otherwise appears to drift slowly toward emptiness. Even if cyclic models remain speculative, they carry a quiet beauty. They transform the vast history of the universe into something resembling a cosmic breath, an endless rhythm of expansion and renewal. And whether or not the universe truly follows such cycles, the thought of those gentle recurring eras adds a layer of wonder to the story of space itself. A reminder that the cosmos may hold possibilities far broader and more rhythmic than anything yet observed. In the earliest moments of the universe, long before stars ignited or galaxies swirled into being, something extraordinary happened. It was quiet in a way that defies ordinary imagination. There were no atoms, no light, no space as we know it, only a newborn universe, small, hot, dense, and teetering on the edge of transformation. And then, in a brief and astonishing instant, the universe stretched. Not slowly, not gently at first, but with an almost impossible rapidity. This moment is known as inflation, the universe's first great widening, a silent event so brief that it took place in a time far too small to describe in ordinary words. To picture inflation, it helps to set aside every intuition built from everyday experience. Nothing in ordinary nature expands in the way the universe did then. Inflation was not an explosion, and it was not a slow unfurling. It was more like a sudden release of tension, a vast smoothing of the cosmos that reshaped everything to come. In a fraction of the earliest second, the universe grew from smaller than a subatomic particle to something enormously larger, still tiny by cosmic standards, but vast compared to its beginnings. And all of this happened in an interval so short that it feels more like poetry than physics. This rapid expansion was driven by a kind of energy woven into the early universe. Whatever form that energy took, it had an astonishing property. It caused space to expand exponentially. Each moment of inflation doubled the size of space, then doubled it again and again and again. With every doubling, the scale increased at a pace that defies typical comprehension. If one could have watched from a safe vantage point, which no vantage point existed yet, the universe would have seemed to balloon outward faster than any light or signal could travel. But again, this did not break any cosmic rule, because nothing was moving through space faster than light. Space itself was stretching. This is one of the reasons inflation feels so strange. It operates on a level of nature rarely encountered in human life. During inflation, distances expanded faster than any object could ever move under its own momentum. It was a transformation not of things in space, but of space itself. And because this happened so early, it imprinted a kind of calm uniformity across the cosmos. Regions of the universe that were once close enough to influence each other were stretched far apart, carrying with them the same initial conditions. A gentle metaphor helps here. Imagine a smooth sheet of cloth that has a few tiny wrinkles in it. If the cloth is stretched quickly and evenly, the wrinkles flatten. Inflation did something similar. Before inflation, the universe contained tiny variations, differences in density so small they would have been nearly impossible to detect. When the universe stretched, These tiny ripples were spread across enormous regions. Inflation did not erase them, it expanded them, and because they were small but not zero, they became the seeds of everything that followed. Those faint ripples stretched across space became the basis for galaxies, clusters, and cosmic structure. Where the density was slightly higher, gravity later gathered matter into clumps. Where it was slightly lower, vast voids emerged. Inflation took the tiniest quantum fluctuations and magnified them to cosmic scales, creating the quiet scaffolding on which the entire universe would build its future. Another gentle consequence of inflation is the uniformity of the cosmic microwave background. This ancient light, a faint glow left over from the early universe, looks almost the same in every direction. Its temperature varies by only tiny fractions of a degree. Without inflation, such uniformity would be difficult to explain because distant regions of the sky would never have been close enough to interact or share information. Inflation solves this by showing that these regions were once close, before they were pulled apart by the universe's first great stretch. Inflation also explains why the universe appears nearly flat. When space expands rapidly, any initial curvature becomes diluted. Just as blowing up a balloon makes a small patch appear flatter, inflation stretched the universe so dramatically that any hint of curvature was smoothed out. This is why measurements of the cosmic microwave background show a universe that behaves, on the larger scales, like an almost perfectly flat expanse. The beauty of inflation lies not in its speed or scale, but in its gentleness. It created a universe that is smooth, balanced, and wide enough to support everything we see. It laid the groundwork for stars to ignite billions of years later, for galaxies to form slowly from swirling clouds of matter, and for planets to coalesce around those stars. Without inflation, the universe might have been chaotic, uneven, or fragmented. Instead, it became a place with structure, uniformity, and the potential for complexity. It is tempting to imagine inflation as a dramatic moment, but it was not an explosion or a burst of light. There was no sound. There were no objects to fling outward. Inflation was quiet. It operated on the invisible scaffolding of space-time, stretching the universe with a smoothness that still echoes through cosmic history. Even though inflation lasted for an incredibly short time, its influence never faded. Every galaxy, every cluster, every filament of matter traces its lineage back to that first brief expansion. After this short interval, inflation ended. The energy driving it transformed, reheating the universe and filling it with particles, radiation, and the familiar ingredients of the cosmos. This transition, from inflation to the hot, dense plasma of the early universe, is sometimes called the reheating phase. It marked the beginning of the universe as a dynamic environment filled with matter and light. From that point on, expansion continued at a far slower, gentler pace, shaping the universe in ways that feel familiar compared to its earliest moments. Although inflation is widely accepted as the best explanation for the early universe's behavior, it remains a frontier of cosmological understanding. Scientists know that something like inflation must have happened because the universe bears its fingerprints everywhere. Yet the exact mechanism remains mysterious. What caused inflation? What ended it? What form did the driving energy take? These questions linger, not in tension, but in quiet curiosity. The universe has given us clues, but it has not revealed every detail. There is something poetic in this mystery. Inflation is one of the most powerful ideas in cosmology, yet it is also among the most elusive. It tells a story that begins with almost unfathomable rapidity and ends with the slow, patient expansion we observe today. It invites us to reflect on how deeply interconnected the universe is, that the structure of galaxies, the glow of ancient radiation, and the shape of space itself all trace back to a silent event in the universe's childhood. When imagining inflation, it is helpful to think not of speed or violence but of smoothness, a quiet unfurling, a gentle widening, a moment in which the universe prepared itself for all the complexity to come. Inflation did not roar, it whispered, and that whisper shaped everything. In this calm picture of the early cosmos, the universe's first great stretch becomes not a puzzle to solve urgently, but a scene to wander through slowly, appreciating how something so brief could leave such a lasting imprint. Inflation is a reminder that even the most dramatic changes can happen in silence, and that the universe's deepest transformations often unfold in ways far beyond ordinary experience. This first great stretch set the stage for stars, planets, galaxies, and life. It ensured that the universe was smooth enough to expand gently, yet varied enough to form structure, and as space continues to widen today, it does so on the foundation laid in that fleeting moment, an opening movement in the long, quiet symphony of cosmic evolution. When people first hear that the universe is expanding, a natural image comes to mind, something growing outward from a center, perhaps like ripples spreading from a stone dropped into a quiet pond, or a balloon swelling from a single point. It feels intuitive to imagine the cosmos pushing outward from some central origin, but the real behavior of the universe is far more subtle, far more elegant, and far more peaceful than that picture suggests. Expansion does not begin at a point and move outward. It happens everywhere at once. It unfolds uniformly, with no center, no edge, and no outside into which it expands. And understanding this gently changes the entire way the cosmos is imagined. To begin, imagine the universe not as an object floating in space, but as space itself. The expansion is not something that pushes into a surrounding emptiness. It is a gradual stretching of distances inside the universe, the quiet widening of the network of relationships that define where galaxies sit relative to each other. There is no central point because every location participates equally. The expansion is woven into the fabric of reality, not imposed on it from outside. A simple image helps. Picture a long sheet of patterned cloth covered with evenly spaced dots. If the cloth stretches, every gap between dots widens evenly. No dot sits at a privileged position. No dot is the origin of the stretch. The cloth expands everywhere at once. And if you were standing on one of the dots, it would appear as though all the others were moving away from you, even though you are not special or central in any way. This is how expansion feels to every galaxy. From any vantage point, the rest of the universe seems to drift away. Now picture the same cloth, but imagine you cannot see its edges. Imagine it stretches so smoothly and evenly that the entire surface appears infinite. That is much closer to the universe we inhabit. Even if the universe is finite in some deep geometric sense, its expansion does not behave like an object growing into something larger. It behaves like a space that stretches internally, changing distances between everything within it. This is why every galaxy sees the same pattern. If you could stand in a distant galaxy and look back toward the Milky Way, you would observe the same gentle drift. Nearby galaxies would appear close and calm. Very distant galaxies would appear to move away more quickly. The farther you look, the faster they seem to recede. This symmetry is not a trick or illusion. It is a natural consequence of expansion occurring everywhere with the same quiet steadiness. Another image helps make this uniformity intuitive. Imagine a rising loaf of bread scattered with raisins. As the dough expands evenly in all directions, the raisins drift farther apart. From the perspective of any raisin, the others appear to move away. No raisin is the center, and none sits at the edge. The dough's expansion is internal, not outward into something else. The universe is not a loaf of bread, of course, but expansion works in a similar way. The galaxies are not flying through space like raisins hurled outward. The dough, space itself, is stretching between them. This leads to a gentle but important point. Expansion does not need to occur into anything. In everyday life, all expanding things grow into surrounding space. Bubbles in water expand into the water around them. Balloons expand into the air. Gases expand into available volume. But the universe is not in something larger. Space is not a substance sitting inside another medium. There is no external region for the universe to push into. Expansion is not a movement outward. It is a change of scale within the universe itself. This is one of the reasons cosmologists describe the universe as isotropic and homogeneous on large scales. Isotropic means it looks the same in every direction. Homogeneous means it has the same large-scale structure everywhere. These terms sound technical, but they simply reflect the peaceful uniformity of expansion. There are no privileged places, no cosmic north or south, no region that expands faster or slower. The universe, when viewed across immense distances, behaves like a perfectly even fabric. Of course, on smaller scales, the universe looks anything but uniform. Galaxies gather into clusters. Clusters gather into filaments. Huge voids stretch between them. Some regions contain rich structures, while others are almost empty. But these variations do not break the overall uniformity. They are like ripples on a calm lake. The lake as a whole still feels level even though the surface has texture. On cosmic scales, the texture becomes insignificant, and the uniformity of expansion becomes clear. This behavior also explains why there is no measurable center of the universe. If expansion had a point of origin inside space, the galaxies closest to that center would behave differently from those farther away. Some regions would expand faster, some would expand slower. The pattern would reveal a direction of flow. But what astronomers observe is the opposite. Every region sees the same relationship between distance and recession. This is exactly what is expected when expansion is everywhere, not somewhere. It is fascinating to consider that even the earliest universe behaved this way. During the period of inflation, space expanded not outward but inwardly, within itself, stretching tiny quantum fluctuations into seeds of structure. When the early universe cooled, the expansion slowed, but the uniformity of the stretch remained. All of cosmic history, every galaxy formation, every drift of clusters, every red-shifted photon sits within that quiet, uniform widening. Another image helps capture this behavior. Imagine a vast, gently inflating balloon, but imagine you live not on its outside surface or inside its volume, but as a two-dimensional being living on the balloon's surface itself. As the balloon inflates, every point on the surface drifts away from every other point. Yet none of those points is the center of expansion. The center is not on the surface at all. The inflation happens in a higher dimensional sense that the surface dwellers cannot experience directly. In the same way, the expansion of the universe does not point to any center inside the universe. It is a behavior of space-time as a whole. One of the quietest misunderstandings about expansion is the idea that galaxies must be moving through space to create the illusion of everything drifting apart. But galaxies are not rushing outward through a pre-existing void. They sit mostly still in their local frames. What grows is the distance between them, not because they are fleeing one another, but because the space between them gently increases. The elegance of this becomes clear when looking at distant galaxies. The ones twice as far away appear to recede twice as fast. The ones 3 times as far away recede 3 times as fast. This proportional behavior arises naturally from uniform expansion. If every region of space stretches by the same tiny fraction over a given time, then the more regions of space lie between 2 galaxies, the more total stretching happens. This uniformity explains why the universe appears almost perfectly smooth at the larger scales. If expansion were uneven, galaxies would clump and distort in chaotic ways. Light would bend strangely. The cosmic microwave background would look lopsided. Instead, everything reveals a quiet symmetry, a sense that the universe is expanding like a calm breath that fills every part of the lungs equally. In a universe like this, no place is special. No vantage point is privileged. Every observer, no matter where they are, will see the universe widening in the same pattern. This is one of the most philosophically soothing features of cosmology. The cosmos makes no distinction between here and there. Everywhere, expansion unfolds in the same patient way. So when picturing the universe growing, imagine not an explosion or an outward push, but a gentle stretching occurring everywhere, constantly, silently. Imagine galaxies anchored like lanterns on an ever-widening ocean, each one glowing quietly while the water beneath them expands. Imagine that no lantern sits at the center. Imagine that lanterns do not travel outward. Instead, the surface itself grows between them. Expansion is not a direction. It is not a wind. It is not a journey outward from a single point. It is a quiet change in the scale of the universe itself, a behavior that occurs everywhere at once, shaping the cosmos into the wide, serene expanse we see today. Light is one of the most faithful travelers in the universe. A photon can leave a star, drift through silent stretches of space for billions of years, and eventually arrive in the lens of a telescope or the back of an observing eye. It does not tire, it does not slow, it does not age in the way matter does. Yet as the universe expands, light changes, it stretches, it softens, it reddens. The expansion of space gently transforms every ancient photon, marking it with the signature of the distance it has travelled and the history it has crossed. This soft transformation is known as redshift. It is one of the most beautiful and intuitive effects of expansion, because it allows us to read the story of the universe directly from the light that reaches us. To understand it is to imagine light not as a rigid beam, but as a delicate wave, able to grow and lengthen as the water beneath it quietly widens. Imagine a simple wave drawn on a smooth sheet of fabric. As the fabric stretches, the wave stretches with it. Its peaks drift farther apart. Its rhythm slows. It becomes longer and gentler without losing its identity. A photon travelling through the universe behaves in much the same way. Its wavelength stretches because the space through which it travels expands beneath it. If the light leaves a galaxy with a certain colour, that colour shifts by the time it reaches us, stretched into redder, softer wavelengths by the widening of space. The universe does not pull on the photon. It does not drag it or deform it in the way moving matter might. Instead, the space that carries the photon grows. The journey becomes longer in a deep, quiet sense. And as a result, the photon's wavelength grows as well. Its colour shifts, its energy drops, and this gentle fading encodes how far it has come. A photon that has travelled for a long time carries the imprint of an older universe. When it first left its source, the distances between galaxies were smaller. Space was denser. The universe was warmer. As the photon moved outward, space expanded, stretching the photon as naturally as a tide stretches ripples on its surface. By the time the photon arrives, it has become a record of both the place it came from and the history it crossed. This idea becomes even more vivid when considering the cosmic microwave background, the oldest light we can see. When it was first released, this light blazed as a brilliant glow, far hotter and brighter than anything we see today. But across more than 13 billion years of expansion, its photons have stretched into microwaves, carrying the faint warmth of an infant universe now cooled to almost absolute darkness. This dim glow wraps the entire sky in a uniform pattern that reflects the earlier structure of the cosmos, a quiet relic of a time when galaxies did not yet exist. The calming concept of aging light emerges naturally from this behaviour. A photon does not age like a living thing, but it changes. Its wavelength becomes a gentle record of cosmic time, a sign of how long it has travelled. The farther away a galaxy is, the greater its redshift, because the photon has been stretched more. The universe has expanded more since it left, and so, by measuring redshift, astronomers measure both distance and time in a single elegant step. This creates an extraordinary connection between space and history. When you look at a distant galaxy through a telescope, you do not see it as it is now. You see it as it was long ago. The light has been travelling across expanding space, stretching with every passing moment. Its redness reveals not just how far the galaxy sits from us, but how long the light has been on its journey. A galaxy with a small redshift is nearby in cosmic terms. Its light is relatively young. A galaxy with a large redshift is far away. Its light is ancient, stretched into deep, gentle shades of red and beyond. In this way, the expansion of the universe turns light into a cosmic time capsule. Every photon is both a messenger and a historian. It carries with it the story of the universe's growth, written in the length of its wave. To imagine this stretching more intuitively, picture a runner on a treadmill. The runner moves forward with steady steps, but the treadmill's belt slowly stretching beneath them would increase the distance they must cover. If the belt stretched as they ran, their journey would become longer without their speed changing. In a similar way, a photon moves steadily at the speed of light, but the space between its starting point and its destination grows. The photon does not move more slowly. The path lengthens, its wave stretches in response. A gentle result of this stretching is the loss of energy. Light with a longer wavelength carries less energy than light with a shorter wavelength, but this loss is not wasteful. It is simply a natural effect of travelling through an expanding universe. Energy is not destroyed, it is diluted, spread across more space, softened by the stretching of the photon's waves. This softening becomes especially moving when imagining extremely distant galaxies. Their light leaves in vibrant colours, blues, whites, ultraviolet hues, and by the time that light arrives, it has reddened into gentle tones of infrared. The universe has carried the light for billions of years, and the expansion has quietly transformed it. What arrives through the telescope is a whisper of what once was, a softened memory of colours that shone long before Earth existed. Redshift also helps astronomers map the universe. Because the expansion is uniform, more distant galaxies show greater redshift. This proportional relationship gives rise to what is called the redshift distance connection. By measuring how much a galaxy's light has stretched, astronomers learn not only how far away it is, but also how the expansion rate has changed over time. This is how scientists discovered that the expansion is accelerating. Distant galaxies showed more redshift than expected if the expansion was slowing down. Their light revealed the quiet effect of dark energy on the fabric of space. It is fascinating to consider that without redshift, the entire story of the universe's history would be hidden. No telescope could reveal how far away galaxies truly are. No observation could show how fast the cosmos expands. The ancient microwave glow that fills the sky would make no sense. Redshift is the thread that ties together distance, time, energy, and expansion. It is the quiet language of the universe, spoken by the soft transformation of light. The emotional weight of redshift comes from its gentleness. There is nothing violent about the process. Light is not stretched by collision or turbulence. It lengthens simply because the universe breathes, and in that stretching lies a record of everything that has happened in the cosmos since the photon began its journey. When thinking about redshift, imagine a lantern drifting across a calm lake. Its reflection stretches across the water as the ripples widen. The lantern itself remains unchanged, but the reflection gently adapts to the motion beneath it. A photon behaves the same way. It stays perfectly itself, yet its wavelength adapts to the growing space through which it moves. Even now, as you listen, light is stretching all around you. Photons arriving from galaxies far beyond the Milky Way are reddening in real time, adjusting to the quiet expansion of space. Their ancient journeys continue wave by wave, second by second, carried gently along by the universe's slow, patient widening. And when that light finally reaches us, it brings with it more than colour. It brings the story of where it has been, how long it has travelled, and how much the universe has changed in the meantime. It is a kind of cosmic memory, written not in words but in wavelengths, soft, stretched, and glowing with the quiet history of the expanding cosmos. In an expanding universe, distance is never just distance, it is also time. Every step outward into the cosmos is a step backward into history, because the farther away something is, the longer its light has travelled to reach us. This gentle connection turns the night sky into a kind of time machine. Each faint glow carries a story from a different era, each smudge of distant starlight a window into an age long gone. The expansion of space does not simply widen the universe, it stretches the timeline we can see, giving us a view that reaches not just across unimaginable distances, but across unimaginable years. To understand this, imagine standing on a quiet shoreline at sunset. The light reflected on the water reveals what the sky looked like moments ago. The farther out the reflection, the older the moment it contains. The universe works with similar simplicity. Because light takes time to travel, every distant object shows us not just where it is, but when it was. A galaxy 1 billion light-years away appears as it was 1 billion years ago. A galaxy 10 billion light-years away appears as it was 10 billion years ago. The farther away the galaxy, the deeper into the cosmic past we look. Expansion adds an extra layer of dreamlike beauty to this relationship. As space stretches, the light travelling through it stretches as well. The waves lengthen, the colours soften. Ancient ultraviolet light from brilliant newborn stars becomes gentle red or infrared glow by the time it reaches us. This reddening does not blur the past, it decorates it. It reveals how much the universe has changed since the photons began their long journey. Each stretched wave is a quiet reminder of the space the photon crossed and the time that has passed. This means the night sky is not a picture of the universe now. It is a layered portrait with nearby stars showing the present and distant galaxies showing the past. The more distant the galaxy, the younger it appears. Not younger in the sense of vibrant stars or shorter lifespans, but younger in cosmic terms, living in an epoch when the universe itself was smaller, warmer, and denser. Looking outward becomes a way of looking backward. Imagine gazing through a telescope and seeing a faint reddish smudge. That smudge might be a galaxy whose light left when the universe was a small fraction of its current size. At that distant time, galaxies were still forming. Stars were younger and hotter. The cosmic web was still weaving itself together. When we observe that smudge, we are watching a moment from deep time, an era so ancient that everything familiar, from the Milky Way to Earth, lay far in the future. As distances increase, the effect becomes even more profound. Some of the oldest light we can see comes from galaxies that formed when the universe was only a few 100 million years old. Their glow has travelled for more than 13 billion years, stretched and softened by all the expansion that took place along the way. These galaxies look small and irregular, like bright sparks in a dark room. They are glimpses of a cosmos still learning to build structure, still gathering gas into stars, still shaping the patterns we see today. And beyond those galaxies lies the cosmic microwave background, the oldest light of all. Its photons began travelling when the universe was still opaque, a glowing fog of particles. When that fog cleared, the photons scattered freely, setting off on journeys that would last for nearly the entire history of the cosmos. When they finally reach us, they bring with them a whisper of the universe as it was in its infancy, long before galaxies existed. Expansion has stretched these photons so gently that they now glow in microwaves rather than visible light, carrying the signature of a time so ancient it feels almost mythical. The dreamlike sense of cosmic time travel comes from recognizing that everything we see is frozen in the moment its light began the journey. When we look at nearby stars, we see moments from years ago. When we look at distant galaxies, we see scenes from billions of years ago. If expansion were not happening, if space did not stretch and light did not redden, we would lose access to this ancient record. The night sky would be flatter, younger, and far less informative. Expansion creates the distances that preserve the past. It also shapes how we interpret that past. Because distant galaxies are moving away faster, their light is stretched more, their colours shift further into the red, their shapes appear more delicate and blurred by the long journey. Expansion shapes not just what we see, but how we understand the story behind the sight. A galaxy with a strong redshift is not merely far away, it is ancient. Its light carries the memory of a universe still learning to form its first structures. In this sense, expansion turns the night sky into a library of cosmic history. Each photon is a tiny page, each galaxy is a chapter, each deep field observation is a window into an older era of reality. The expansion of space writes time into light, encoding the universe's memoirs into the waves that reach our eyes. The emotional tone of this idea is gentle rather than dramatic. There is no rush and no urgency. The universe sends its messages patiently, letting light drift for billions of years, and when that light arrives, it shows not only where the galaxy once was, but how the universe has changed in the meantime. A photon's stretch becomes a quiet record of the expansion, a sign that the universe has widened considerably since the photon first set out. To appreciate this fully, imagine the universe as a vast, dimly lit hall. The nearer lights show the present moment. The mid-range lights show earlier scenes. The farthest lights illuminate the earliest chapters, flickering faintly from unimaginable distances. To walk through the hall would be to walk through time. To look out across the hall would be to see history laid out in layers. This is what astronomers experience when they peer deeper and deeper into the cosmos. They are not seeing farther in space alone. They are seeing farther in time, stepping backward through the universe's memories. And there is something quietly humbling in the fact that the universe reveals its past voluntarily. It does not hide its early days. It offers them up through ancient light, asking only that we know how to recognize the signs. Expansion does not erase the past. It preserves it, stretching the light so gently that the information remains intact. This connection between distance and time also means that the farther we look, the more we approach the beginning. In the deepest fields captured by modern telescopes, humanity has seen galaxies that formed when the universe was tiny compared to today. These galaxies appear fragile, often chaotic, shaped by early cosmic conditions. Their light is so stretched that it arrives on Earth as long, soft waves. Yet through this stretching, we see the universe's youth with extraordinary clarity. Even though expansion ensures that many distant regions will eventually slip beyond reach, the light already on its way will continue travelling until it arrives. Each photon completing its journey becomes a tiny portal into the past, a fragment of cosmic memory that expansion has carried through billions of years. So when glancing upward at night or gazing at photographs of distant galaxies, it is worth remembering that expansion has allowed humanity to become observers of time itself. The universe does not merely expand outward, it expands backward, giving us a view into eras long vanished. In its widening, the cosmos opens windows into its earliest moments. Through redshifted light, we see the past written into the present, each distant glow, a story carried across the slow, patient breath of the universe. And so expansion becomes not just a physical behaviour, but a gift, a way of letting us glimpse the moments that came before, of letting us drift gently through time simply by looking at the sky. The question sits quietly beneath everything we've explored so far, like a soft thread running through the fabric of the cosmos. Will the expansion of the universe ever end? It is a question that carries both scientific depth and emotional weight. It asks not only about the future of galaxies and the destiny of space, but also about the long arc of cosmic time, reaching far beyond the lifespan of stars, planets, or anything that feels familiar. And while scientists have gathered many clues, the final answer remains gently out of reach, held in the subtle behaviour of forces we still do not fully understand. To begin, it helps to look at what the universe is doing right now. When astronomers measure the light from distant galaxies, they find that those galaxies are drifting away faster than expected. The farther away they are, the faster they recede. This pattern itself is not surprising in an expanding universe. But what is surprising is that the rate of expansion is increasing. Galaxies are not just separating, they are separating at an accelerating pace, like lanterns drifting across a widening lake that grows larger with each moment. This acceleration was discovered in the late 1990s by studying the light from distant stellar explosions known as supernovae. These bright events act like cosmic lighthouses, revealing how far away their host galaxies are and how the expansion has changed over time. The measurements were unmistakable. The expansion was not slowing under gravity's pull, it was speeding up. Something was encouraging the universe to widen ever more quickly. This something is what scientists call dark energy. It is not dark in the sense of shadow or gloom, it is dark in the sense of unknown. Dark energy appears to be a property of space itself, a gentle pressure that fills the universe and encourages expansion. It does not gather into clumps, it does not drift through space. It behaves as a quiet, uniform backdrop, the same everywhere, influencing everything with the same soft persistence. If dark energy remains constant, the universe will continue expanding forever. The widening will accelerate gradually, pushing distant galaxies farther and farther apart. In the far future, the cosmic horizon will grow, and more galaxies will drift beyond reach. The universe will become increasingly spacious, with islands of stars drifting in ever larger oceans of darkness. This long, slow unfolding would not be dramatic. It would be calm, inevitable and steady, guided by the subtle influence of dark energy. Yet the truth is gentler and more uncertain. Dark energy may not be constant. It may change. It may fade. It may transform in ways we cannot yet predict. Because dark energy cannot be seen directly and behaves differently from anything known, its long-term behavior remains one of the greatest open questions in cosmology. If dark energy weakens over time, the acceleration of expansion could slow. The universe would continue expanding, but more gently, perhaps settling into a slow drift rather than an accelerating race. Expansion might continue forever at a calm, steady pace, without the increasing separation that defines the current era. If dark energy fades completely, the universe would eventually be governed once more by gravity and the momentum of earlier expansion. Depending on the balance of those forces, several peaceful futures become possible. Expansion could continue forever at a constant rate. It could slow to a near standstill, or, in more speculative scenarios, it could gently reverse, beginning a slow contraction that unfolds over spans of time so immense they defy ordinary understanding. This potential reversal, often called a big crunch, is not a prediction. It is merely a possibility, a path the universe could follow if dark energy behaves in certain ways. In such a future, distant galaxies would stop drifting away. Over trillions of years they would begin drifting inward. The universe would grow denser and warmer, gradually folding back into itself. Yet even this path is not an ending in any dramatic sense. It would unfold with the same cosmic patience that characterizes the universe now. Another possibility lies at the edges of more imaginative theories, that the universe might oscillate, moving through cycles of expansion and contraction. In these rhythmic models, the expansion we see today is just one phase in an unending sequence. After a long expansion, the universe might contract, then bounce into a new era. These ideas remain speculative but offer a poetic sense of renewal. as though the cosmos breathes in epoch-spanning unimaginable lengths of time. Despite all these possibilities, every piece of reliable evidence points toward a universe that will continue expanding indefinitely. The patterns of redshift, the smoothness of the cosmic microwave background, the behavior of galaxy clusters, the measurements of distant supernovae, all whisper the same quiet message. Expansion is accelerating, and there is no sign that this behavior will stop. Yet the lack of a final answer does not bring anxiety. It brings wonder. The universe is vast not just in scale, but in possibility. Its long-term behavior is shaped by ingredients we only partially understand. Dark energy remains one of the most profound mysteries in science, a reminder that even after centuries of discovery, the cosmos holds secrets that encourage humility. There is something comforting in this uncertainty. It reminds us that the universe is not a completed story. It is still unfolding, still expanding, still surprising. The question of whether expansion will ever end is one of those rare cosmic questions with no urgent answer, because the timescales involved stretch so far beyond human existence that they create a kind of peaceful distance. Whether expansion continues forever or changes course trillions of years from now, the universe around us will drift along at its own serene pace. For now, expansion defines the cosmic landscape. It shapes the structure of galaxies. It stretches the light from distant stars. It creates horizons that drift farther away each moment. And through all of this, it offers a quiet sense of motion, a slow, steady widening that began in the universe's earliest moments and may continue for all time. To ask whether expansion will end is to step into the future of the cosmos itself. And although the future remains open, the present offers a clear and calming picture. The universe is growing, gently and persistently, shaped by forces that operate on the grandest scales imaginable. The expansion, whether eternal or temporary, gives the cosmos its shape and its story. It may be that the universe expands forever, growing more spacious with every passing moment. It may be that dark energy changes and the future unfolds along a different path. Or it may be that the cosmos follows a rhythm we have not yet understood. Whatever the answer, the question itself opens a quiet doorway into wonder, a reminder that the universe is not only vast in space, but vast in mystery, offering endless room for curiosity, reflection, and gentle awe. As the long arc of the universe stretches back into stillness, you can begin to let the distances fade from your mind. All the drifting galaxies, all the widening spaces, all the quiet mysteries that hang at the edge of what is known, they can settle now, gently, like dust drifting down through a soft beam of afternoon light. You have followed the cosmos outward, across unimaginable distances, and now it is time to return to the quiet place where you rest, wrapped in the calm of the present moment. The universe you have explored tonight is vast beyond measure. Galaxies drift like lanterns on an ever-widening sea. Space stretches so steadily that even ancient light carries the imprint of its long journey. Horizons slip away. Distant eras glow faintly from across time. The motion of the cosmos is so slow, so patient, so continuous that it becomes a kind of cosmic breath, one that has been rising since the earliest moments of existence and may continue long after every star has dimmed. And yet, for all its size and age, the universe remains woven into this single moment with you. Every photon that reaches your eyes, Every quiet image captured by telescopes, every map of distant galaxies, all of it is born from the same expansion that carries the cosmos forward. The history of the universe, with all its stretching and drifting, is contained in the light that gently falls upon this instant. You do not need to hold all of that in your thoughts. It is enough simply to know that the universe continues unfolding, one soft widening at a time. The galaxies that drift away from us do so without haste. They do not push or struggle. They simply follow the shape of space as it grows beneath them. Even the most distant ones, slipping toward horizons beyond reach, move with a calm inevitability. And in their fading light, you can sense something deeply peaceful, a reminder that the universe does not rush. It does not force. It does not worry over its destination. It expands because expansion is woven into what it is. Perhaps there is comfort in that quiet certainty. The universe grows, not loudly, not suddenly, but with a persistence as soft as the rise of dawn. The distances between galaxies increase. Ancient light stretches into gentler colours. Time itself becomes something spacious, something wide, and through all of it there is a deep and steady calm, an assurance that change can be both immense and peaceful, both powerful and slow. When you think back to the earliest moments of the cosmos, to the brief instant when inflation smoothed the universe into something uniform and open, it becomes clear how profoundly the universe has always been shaped by stillness as much as by motion. The great first stretch did not roar. It whispered. It prepared the universe quietly, setting the stage for everything that followed. And tonight, as you rest, you have traced the echoes of that whisper across billions of years of cosmic history. The expansion may never end. It may continue for all time, carrying galaxies farther apart and dimming the sky into deeper and deeper calm. Or perhaps, far beyond any future we can imagine, the forces that guide expansion will shift, and the cosmos will follow a path no one has yet conceived. There is no urgency in finding the answer. The uncertainty itself is gentle. It leaves room for wonder, space for curiosity, and a sense of peace in knowing that the universe is still writing its own story. And while the cosmos continues to widen, you can let your world become smaller for a while. Let your breath fall into a slower rhythm. Let the thoughts of distant galaxies dissolve, leaving only the soft awareness of where you are, quiet, safe, and resting. The universe is vast enough to hold its own questions. You do not need to carry them with you. All the light you have imagined tonight, ancient photons stretched across space, fading galaxies at the edge of vision, the soft glow of the early universe, has travelled across unimaginable distances to reach this moment. And now, as you settle more deeply into rest, you can let that light drift away, knowing its story will continue quietly without you. You have followed expansion across its long, gentle path. You've imagined horizons slipping outward, galaxies drifting apart, and the deep future of a universe that may continue growing forever. Now, let the cosmos recede into the background, becoming a soft hum behind your thoughts. As the universe drifts outward, may you drift inward toward a deeper stillness. May the quiet of the cosmos settle around you like a soft blanket, and may you find rest in the gentle widening of the night.